Check 1 2 3 check. Sound check 1 2 3 check check.
I can hear your sound. Can you hear me? Hello?
Check. A very good afternoon, all of you. We are going to start this program within the next 10 minutes. Thank you so much for coming and gracing the beautiful occasion. Ladies and gentlemen, may I have your attention, please? A very good afternoon and a very warm welcome to 11th India Probiotic Symposium. So, respected chief guest and our guest of honor, Professor Shiv Pillai, Professor N.K. Ganguly, Professor Jeffrey Gordon, Professor Samuel Raj, Professor Tehmeed Ahmed, our esteemed chairpersons, speakers, delegates, senior international colleagues, and our young investigators. We would really like to thank you for taking the time for participating in the symposium, Role of Gut Microbiota and Probiotics in Reducing Viral Infections and Mechanisms to Combat Them, an initiative of Microbiota and Probiotic Science Foundation India and SRM University, Sonipat, Haryana. So it gives us immense pleasure to welcome you for the series 11th India Probiotic Symposium. The theme of the symposium this year is Role of Gut Microbiota and Probiotics in Reducing Viral Infections, Mechanisms to Combat Them. So, the foundation, in its endeavor to promote research in the area and felicitate talent in the country, had instituted the Young Investigator Award in 2015. The response to this new initiative has been overwhelming, and this year, just like FAST, we are very happy to announce that we have shortlisted 20 young investigators whose abstracts were selected after a stringent evaluation by the governing body members of the foundation. So the posters have been uploaded on this virtual platform and are available for viewing on both the days. So the posters have been evaluated by an international jury, and the best three posters have been awarded the Young Investigator Awards. So the top three young investigators will be making their presentation tomorrow, that is 14th March from 11:30 to 12 noon. So please make sure that you do not miss it. So the presentations of the symposium will also be webcast, and the talks will be archived on the foundation website. So the link of the archived talks will be sent to all the delegates so that the presentations can be viewed again. So we once again thank you, each one of you, for taking time to attend this symposium, and we hope you enjoy the presentations during the next 2 days. So, ladies and gentlemen, we will now proceed for the lamp lighting ceremony, which is a typical tradition in India and marks the commencement of any important event. So, we are all overwhelmed. We are attending this important event. So, I want, before this lamp lighting, everyone should applaud as we are proceeding towards the inauguration. Everybody, please put your hands together. Thank you so much. We are honored to have among us Professor Nirmal Kumar Ganguly, now Professor V Samuel Raj, Professor Anil Kumar Srivastav, Dr. M.S. Chauhan, and Dr. Amulya Pandya. I request all the people to kindly come forward to light the lamp, please. I request all the sirs. Requesting all the honorable people to kindly come forward and proceed with the lamp lighting. Everybody should applaud. May I request all the esteemed dignitaries to please be seated on the stage for the inaugural session. So, ladies and gentlemen, we now have to proceed for the welcome address. So, may I now request Professor Nirmal Kumar Ganguly, the President of the Gut Microbiota and Probiotic Science Foundation India, to kindly deliver the welcome address. So, I would like to highlight Professor N.K. Ganguly needs no introduction. He is a former Director General of the Indian Council of Medical Research, former Director PGI Chandigarh, and National Institute of Biologicals, former President of the National Academy of Medical Sciences, Indian Science Congress JPI MER Puducherry. He is Fellow of Imperial College and the Royal College of Pathologists and the Tropical School, London, Fellow of all the Medical and Science Academies in India, Third World Academy. So he's member of the advisory committee to the Minister of Health on COVID-19. Currently, he is president of the Gut Microbiota and Probiotic Science Foundation India, Immunology Foundation of India, and Indian Society of Translational Research. He has published more than 775 research papers and supervised or co-supervised 130 PhD candidate and more than 20 book chapters. So Professor Ganguly has been honored with 7 international and 113 national awards, along with the prestigious Padma Bhushan Award in the field of medicine for the year 2008. It's my immense pleasure to call sir on the stage. Everybody, please put your hands on. Very warm welcome.
She is much taller than me. So welcome all the esteemed guests and participants on behalf of the Gut Microbiota Probiotic Foundation, as well as the governing board and scientific advisory board of the foundation. I also welcome Dr. Srivastav, who was the former director of NDRI, as well as now he's a board member of the board of the selection of the agriculture university scientists. As then we have Dr. Chauhan, who is the current director of NDRI. We have Dr. Amulya Panda, Director of National Institute of Immunology, and our co-sponsor for this, Dr. Samuel Raj, who is the Dean of the SRM University in the Sonipat. I feel very proud that I'm also one of the honorary faculty in the SRM, and so some or other, it's just a coincidence that I'm also very proud of two groups of scientists over here who have now made the name for themselves, of whom I mentored when I retired. One is SGRS or Gangaram Research Unit, and the former Institute of Molecular Medicine. Now they are the Center of Molecular Medicine in Jamia Hamdard. So I'm very happy that several of them have started working on gut microbiota and probiotics. So it gives me a great honor to be amongst with you and present a very different kind of a conference today. Our aim was to, right from the beginning, to promote the science of gut microbiome as well as the probiotics and symbiotics. When we started, this was hardly mentioned in India. And our main job was to some or other bring it into central stage. It has come in the central stage. It has become one of the major driving force of the science at this given moment. And we came to realize that these are the guys who are actually moving us. We are not moving them. These are the guys who are moving us and determine whether we want to remain healthy or we want to remain in problem, dysbiosis, I will say, not gut dysbiosis, total body dysbiosis. So, so how does it how does this science have now got a new life within itself? This was because of two major science drivers. One was the high throughput sequencing. The second, and making it easy for people to do it. Whosoever wants to do it can now do it if they want to wish. The second one was the strong bioinformatic and statistics tool which could find out a meaning out of it. And third driver was creating series of products which have multifunctional activity, or they are pluripotent, so-called pluripotent cells who could drive several parts of the metabolism. And these guys, they might reside in all our mucosal surfaces, in mother's milk, in even in the amniotic fluid. They are omnipresent, reside everywhere. They reside in the environment also. And what we realized, that many of them are driven by the food we eat, the environment in which we live, and we can manipulate them by changing food, changing environment, and changing the way we live. They are also harbinger of a major process of nutrition, whether they are delivered as food, or whether they are delivered as a drug, or whether they are delivered as a pharmaceutical entity. So this year has been a very, very challenging year, in the sense that we thought that we will be coming to our knees, and because of the lockdowns and because of not being able to work in the laboratory. However, it was a surprise. The human animal or human organism, we also are organisms, although we are primates, but we have evolved from organisms, has a tremendous ability to adopt. And as Mr. Darwin taught us, that we can really adopt to any situation, any situation which we encounter, whether it is desert, whether it is North Pole, South Pole, whether it is space, you name it, and we can adopt ourselves. And our microbiome also adopt itself. So they are present in the space vessels, they are present in the satellites. There is a scientist known as Shivaji, who was a student of Dr. Pushpa Bhargav. He thought that they will explore these areas, and they are there, and they are doing functions which we realize or don't realize. It ultimately spells its cost. So whether they are in gut, they can modulate brain. Whether they are in the gut, they can also modulate our immune system. So, so the one of the things which now became very important and challenging, that even though we face these challenges, we found an opportunity also. The COVID infection which hit us taught us that how do we use probiotics to our advantage. And one of the main aim during the COVID infection was that how to really maintain our immune system. Our main apparatus in the adults, and as we move from childhood, the immune system maintenance moves from thymus to the or bone marrow is still important. We don't have bursa fabricius as the birds have, but we have our gut. We have Peyer's patches, we have germinal follicles there, we have the mesenteric lymph glands, and in the spleen we have the penicilloic artery and the total organ, which are in sync and which in which the immune cells circulate with each other, exchange information and exchange vital functions and keep us living and intact. It also creates our gut mucosal health, because many of the cytokine and endocrines, when I was an immunology student, I knew hardly 8, 10 cytokines which were vital. Today there are 65 of them, and they are being monitored, they are being measured, and each one has got a function or several of them has a function together. And this is also monitor, this is also very important for gut immune system, and probiotics actually keeps them intact, keeps them functioning, keeps the pattern seeking receptors of these guys, antigens, they seek out the pattern seeking receptors and ultimately clonally multiply, and they become more multi poly TLR agonists or antagonists. And in this way, they control inflammation also. So inflammation control was central to COVID-19 infection. And these are the guys who can do it. The third very important part was the toll receptor 9 modulation, which actually brings the immunologic function from autoimmune path to an immunologic path. And here, one of the things COVID-19 does, it really makes the aberration of the immune responses. And these aberrations ultimately join to a lot of metabolic paths, of whether these are ACE2 mediated metabolic paths or integrin mediated metabolic paths. Huge amount of number of metabolic paths are mediated through this. This also becomes a very important part of providing nutrition. One of the girls sitting here was discussing, her name is Priyanka. She is sitting over here. One day she was discussing with me that, well, I want to do microbiome. I said, "Beta, what do you want to do with microbiome?" She says that I want to deliver vitamin B12 and see that whether I found that in the mycobacteria, there are several others, vitamin B12 plays an important part. So I said, what about vitamin D? It has also got immunologic significance. It has got importance in COVID. It has got importance in linking the immunologic responses, clavulanic acid pathway, TLR2. It is multidimensional. But this girl was just a greenhorn. She had done her MSc biochemistry and she wanted to do this. So I was very, very encouraged that there are youngsters who are picking your brain, who are putting challenge to you, and they want to work in this. So this is where the science is moving now. It is actually fascinating, huge number of new investigators towards this field. And what an advantage as you look at it. Like one of the things which we have in the COVID-19 infection, that it is the hydrocortisone, the corticosteroids, because they reduce the inflammation very efficiently. But what do? They reduce the interferon functioning. One of the major interferon, which is antiviral, is beta-seron. So they compromise that. They also compromise the major other cell-mediated immune responses. So although they bring down the inflammation, they ultimately create huge amount of other problems. So and there are long haulers in COVID-19 who go on suffering for years, even after they have been so-called cured. And these are the remnant of the host tissue interaction, where you get huge amount of toxicants which are generated. And you cannot go on giving methylprednisolone throughout. All other immunosuppressants, huge number of them were discovered. Even the Regeneron and Eli Lilly discovered, they made several cocktails of the monoclonal antibodies. All of them had, like, if we have an elephant and we are blind people, somebody is touching tongue, somebody is touching the body, somebody is touching something and creating a sense of this. So there was nothing whole which had a multi-dimensional effect, and probiotics are actually providing those effects. And after we came to understand the gut microbiome and gut microbiota, we came to understand it, that this is something which evolves around us, which might be special in those who will respond to COVID-19 infection, or those who will not respond to that. These will be the organism which will protect heart, which might, because of the strong antioxidant activities which they provide, this will keep the nutrition intact in the persons who get actually starved for nutrition during the viral infections. And this will be multiviral, provide multiviral opportunities. Large amount of clinical trials have evolved. One of the other things which we learned during this phase, how to do a very good randomized placebo-controlled clinical trial. It was not possible to do it with the probiotics before, because simply there was no interest in this. And this was very important because we went on interminably debating between ourselves whether these are beneficial or whether these are not beneficial. So even after meta-analysis showed some benefits and other benefits, ultimately when there is a polydimensional activity, there were naysayers and there were yes-sayers, and ultimately the debate went on. So it kept us in business, because like a dermatologist, which I say no pun to dermatologists, they are very good friend of mine and collaborators. Your patient doesn't get cured, your patient goes on paying you money, doesn't call you at the night, and doesn't die. So you are very happy. So this debate, we were not really giving clear-cut answers to this debate. Now it is possible. During this period, we have learned to do this. And we are also getting funded. And the pharma company and other companies who had a disdain on this, majority of the food companies were actually going towards producing these products and providing it to us. These guys have also started taking interest. So I see this particular part will come up as a big opportunity for us and to the whole community who are working in this. We have got lot of scientists who never worked on this, like Amit is sitting here, and he is a die-hard immunologist. He is also talking of microbiota. One of my PhD students, I had not put microbiome in the thesis, and he said, no, please put it. And we had a strong argument with the oncologist, and oncologist ultimately agreed and saw the light of the day and said, okay, let us do it. Problem is with the scientist that this girl has never seen even a bacteria, so what to talk about microbiome. So how do we do this? It is possible to do this now. There are guys who can really work, who have platform technologies, and these guys are ready to work with you if you have a bright idea. So anyone over here, whether you are in the subject or whether you are not in the subject, if you want to do something on this and if you have a bright idea, it is possible to do this. This particular time has also created these opportunities to every one of us. So best wishes to all the communities over here. Majority of us are attending this from from the net. And I welcome also all of them and wish that they were here. We had never done this kind of thing before, but by the time our next meeting comes, all of us will be vaccinated and we will have again the opportunities to be physically present over here and enjoy each other's company and discussion and benefit from each other. We have Dr. Geeta Tilok Kumar here. I didn't know she was former NDRI nutritionist. So we have a lot of nutritionists over here, lot of food technologists over here, food scientists, basic scientists, immunologists, clinicians. We have the whole variety of the people over here, even today physically present here. And this is very good that most of the guys sitting here don't have gray hairs like me. Majority of them, except Selva Pandian, has got black hairs. And so that is also very good. And because they are the future. So wishing you all the best and welcoming you over here. Please enjoy yourself, have a ball. There is some very good speakers over here. In the nutrition, we have Tahmeed over here. Tahmeed has published in the Science, journal Science. He's now the first non-American or non-foreign executive director of ICDDRB Dhaka. He will be with us also. So the nutrition group will also benefit. We have created the palette where everyone will have somebody or a group with which they will relate. Thank you and welcome. And hats off to Nirja. Everything which you see here has been done by her.
Thanks to Professor N.K. Ganguly for the welcome address. Ladies and gentlemen, I would like to highlight we are very honored that over 800 people have joined this symposium online. So now we have to proceed forward. So requesting Professor V Samuel Raj to kindly deliver the opening marks. So Professor V Samuel Raj is working as the Professor of Microbiology and Biotechnology, Director of the Center for Drug Design Discovery and Development, and Dean Academic Affairs at SRM University, Delhi, NCR, Haryana, India. He has established the Center for Drug Design Discovery and Development at SRM University in 2014 with 10 years of R&D experience from two major pharmaceutical giants Ranbaxy and Daiichi Sankyo, and also with more than 25 years international and national research experience in the area of infectious diseases, including virology. So he's a recipient of many awards, including STARS Fellow, Biomedical Leader, Switzerland and Tokyo Biochemical Research Foundation, TBRF Award, Japan. So ladies and gentlemen, please put your hands together for Professor V Samuel Raj. A very warm welcome, sir.
Good evening to all of you. My special and sincere thanks to Professor N.K. Ganguly sir, who is my mentor. In fact, I have the privilege of listening to him for more than 3 decades. One of the very few people have such a privilege. And I'm so happy and I'm very glad to inform you that I am one of the such privileged person who could listen to him. In fact, when he was talking, I was feeling like to listen to him more than that he stopped. But now I have to speak on the opening remarks. That's the reason that I'm standing here. I would like to give my sincere thanks to Professor Ganguly sir again for giving me this opportunity to give the opening remarks. And also I would like to thank a very dedicated and a dynamic person, Dr. Nirja, for giving me this opportunity to give these opening remarks. In fact, last year I was invited to attend this 10th symposium organized by Gut Microbiota and Probiotic Science Foundation. But I never thought that in the 11th symposium, we will be associating with such a great organization and as a host of this 11th India Probiotic Symposium. That's the reason that my heartfelt and sincere thanks to both of them, as well as the foundation governing body members for giving us such a great honor to be part of this prestigious symposium. And also, I'm glad to see Dr. Amulya Panda over here, Dr. Srivastav, Dr. Chauhan. Thank you, sir, for joining over here. It's our privilege to have you over here. And I'm glad to inform you that our Chancellor of SRM University, Delhi NCR, and Vice Chancellor, they convey their best regards and best wishes to all of you, and also the participants. I'm glad to see that more than 800 participants have already joined online and listening to this one. This is a wonderful event which has both offline as well as the online. This is a blessing in the disguise. Though we are not able to gather more than 50, but many scientists around the world could join online and attend this symposium, which is really great. And I would like to recognize the presence of our senior colleagues from our university, the Registrar Professor, Dr. Manish Balla, Dean Engineering Professor H.C. Roy, Dean Law, Professor D. Mukhopadhyaya, Dean Science and Humanities, Professor Rakesh Dubey, and also my colleagues Ramendra, Archana, Arpana, and Anjali. And of course, all the distinguished scientists over here. If I take the names, my time will be over with that. I know that you have done a lot of work, and most of you have done on this particular topic, gut microbiota, and how it helps, how it prevents the infection, and how it can prevent the viral infection. This is a hot topic today. We know that if the microbiome, the microbiota in the gut is disturbed, there is an imbalance in the gut. There are more than 1,000 different types, different species are present in the gut microbiome. If the antibiotics are given, so what happens that there is a disturbance, dysbiosis, imbalance, that causes the sickness. That causes the presence of the pathogenic bacteria. There is one particular bacteria which is called as the Clostridium difficile. There is no external infection due to this Clostridium difficile. That is already present in the gut microbiome. Whenever there is an imbalance, whenever the antibiotics kill the useful, beneficial microorganisms, this particular Clostridium, pathogenic Clostridium difficile, it takes over. And it causes these antibiotic-associated diarrheal diseases. And because of the toxin, even people die. They get the good treatment in the ICU or in the hospital, but because of the infection due to Clostridium difficile, the people could die. That is because of the antibiotics used in the ICU or in the hospital. Unfortunately, many pharma companies, they do not want to work in the antibiotics, antimicrobial drugs. One of the simple reasons is that the return of the investment, because this is not the lifestyle disease. If any drug is coming for the diabetes, inflammatory diseases, arthritis, or any lifestyle diseases, the patients have to take it for a long time. But unfortunately, this will not give a very good return. 5 days to 7 days, the antibiotics, the antimicrobial drugs. And even within that period, many times what happens, the pathogens becomes resistant to this particular antimicrobial agents. And once they become resistant to this particular drug, they are no more useful. And that is one reason that many pharma companies, I worked in a pharma company run by Daiichi Sankyo. They closed the anti-infective units. They keep other units. They ask the employees, they ask the scientists, would like to go to the other unit, anti-inflammation, cancer, some other unit, you are most welcome, you can be there. But you are in love with antibiotics, antimicrobial drugs. Thank you so much. The pink slip is given. So this is what's happening. Even a pharma company like Pfizer, what they do, they buy the drug along with the new antimicrobial drug. They buy, even the company, they close down complete the unit. They keep the drug. And this is not the way to conduct this R&D unit of antimicrobial drugs. Now, due to this COVID-19, there are so many bad things have happened. We know that. But among all the bad things, if we list very few good things, there is interest to develop vaccine against this COVID-19. We know that the world has crossed 111 million COVID cases with 2.6 million deaths. US stands first with 30 million cases. This morning, I was looking into the scoreboard of COVID. There are two news, one good news, one bad news. What was the good news? India has gone from second position to third position. Now Brazil has taken over. That's the good news. The bad news is that yesterday's number of cases were 27,500. It's increasing. From December, and yesterday was the highest number of cases. This is really a bad news. Are we going towards the second wave? We have to wait and watch. That's one of the reasons that we need to wear the mask always. Our people in the market, in other places in the country, they have already declared that the COVID is over. If we don't take precautions, we will suffer a lot. And that's a lesson that we need to learn. We know that vaccine prevents the COVID. And I'm so glad, and all of us are proud that our country is the leader in the vaccine. We have the Covaxin, Covishield, in collaboration with Oxford, AstraZeneca, and many more vaccines are coming. I was talking to Dr. Amulya Panda. He was so happy to share the news that NIA is coming up with a protein vaccine. And there are more vaccines are on pipeline. The companies are coming forward. But what is missing is that the drugs research is not there as much as we need. Vaccine, yes, we are on the right track, but the drugs, we need to do a lot. So many people, they have worked on the drugs, but still, we don't have any successful drugs or combination of drugs to completely cure COVID. So that's where we need the probiotics. Why? What the probiotics they do? As we know that if we use the antibiotics, if we use the drugs, including the antiviral drugs, if it is oral, what they do, they disturb the gut microbiota. As Professor Ganguly sir was talking, the microbes are present all over the body. And I'm sure if you take a swab, keep it in a Petri plate with a media, you will get so much of bacteria. Anywhere, wherever we touch, the skin contains microbes. The lungs also have microbes. There was a cystic fibrosis report. They conducted a study. What they have done was that when they were doing the study, they proved that at the time of birth or after the birth, the microbiome develops at the same time, the gut microbiome as well as in the lungs. But only thing is that in the gut, plenty of microbes, billions of microbes. But in the lungs, it's 10 to 100 microbes per 1,000 human cells. But they develop at the same time. Now we know that in the COVID, some people are admitted in the ICU. Some people, they develop ARDS, acute respiratory distress syndrome. They get the lung infection. The cystic fibrosis studies long back, they proved that there is a crosstalk between the gut microbiomes as well as the lung microbiomes. They communicate with each other. They may be present in different places, but they communicate with each other. Now, in the ICU, so many drugs are given. So many antibiotics are given. There are reports in the COVID patients, many bacteria also become resistant to many drugs because antibiotics are given. So this is the place where the probiotics could help and bring the balance wherever there was imbalance. The main reason the patient they die not only because of this coronavirus, but with the associated diseases. So the probiotics will help to build the immune system. There are so much of studies. Last year, after attending the Probiotic Symposium, the first thing what I've done was that one of my PhD scholar, he is also attending this online. He has a veterinary background. I asked him to study this metagenomics of these microbiomes. You give the fat diet, what happens? You give the antibiotics, what happens? You infect the mice and then give the antibiotics, what happens? And the next stage is to give the probiotics and then see that one. And one of our next target is to give the viral infection. I know that there are so much of studies are going on in this particular aspect. And study what happens that. So what happens during this COVID infection or any viral infection? There is an imbalance in the gut microbiota. So it causes so much of problems within the immune system, and at some point, this organ failure. So that's where we need to bring this probiotics. I'm not saying that probiotics is an alternate for vaccine. I'm not saying that probiotics is an alternate for the drugs, but probiotics will definitely help in this particular, to develop this immune system. So that's what I would like to, give this opening remarks that probiotics exists. Probiotics gives several health benefits, and it induces the gut immunity and takes care of many things. I'm so glad to inform you that we have excellent speakers these 2 days. So in fact, one more session now and tomorrow also, you will hear so much of excellent lectures. So without taking much time, I thank you so much. And especially, I thank Professor Ganguly sir as well as Dr. Nirja and the governing body of this Probiotic Science Foundation for giving us this excellent opportunity. Thank you so much. Have a nice time. Thank you.
Thanks to Professor V Samuel Raj for opening remarks. Now we have to proceed further. Now for the inaugural address. May I now request Professor Shiv Pillai to kindly deliver the inaugural address. But I would like to highlight, Professor Shiv Pillai is a professor of medicine and health sciences and technology at Harvard Medical School. He studied medicine at Christian Medical College in Vellore, completed his PhD and was a postdoctoral fellow with the David Baltimore at the Whitehead Institute and MIT. He has been the recipient of a number of teaching awards at Harvard, include the Irving M. London Award for Teaching. Dr. Pillai coined the term surrogate light chains for the proteins that he identified as part of the pre-B receptor that drives early B cell development. So ladies and gentlemen, please put your hands together as requesting Professor Shiv Pillai to kindly come virtually to deliver the inaugural address.
Hello, can you hear me now? Okay, I'm going to share my screen. I'm going to assume you can see my screen. Interrupt me if you can't. So it's a great pleasure to be here. It's before sunrise here in Boston. And I guess I'm here to provide some balance since I've heard about there being people with gray hairs and people with black hair. I think you want some people with no hair as well. So I'm here for that balance as well. So I'm going to be talking about adaptive immunity and the pathogenesis of COVID-19. And I will, at the end of the talk, bring this towards some of our work with the microbiome as well. So everyone is aware of the fact that we have these spike proteins with receptor binding domains that stand up to bind to ACE2, and that this is a trimeric protein, and you have this unfolding and the standing up conformation. And the way the system works is, of course, that TMPRSS2, a protease on the host cell, cleaves off the head of the spike when it binds to ACE2. And then you have a spring released underneath, which is basically the fusion domain, which allows the fusion of the viral membrane with the host membrane, thus allowing entry. And one of the possible reasons why we have had such a severe pandemic in so many parts of the world is that as populations of the world, we did not have many antibodies or any antibodies that provided any sort of neutralization before the pandemic. And this created the initial severity. And of course, the virus has some unique features as well that we will talk about. Now, if you think about innate immunity and divide it into two broad categories, one being inflammation, which in a very generic sense, you can think of as being more protective against bacterial and fungal infections. And you think of the antiviral state, which is more directed towards viruses. This is not absolute, but it's relatively true. Then when we think about COVID-19, we have to think in those contexts. We think of a failure of the antiviral state and excessive inflammation. Now, 10 of the 29 genes of SARS-CoV-2 prevent the induction of type 1 interferon in infected cells. So as a result of this, the antiviral state is largely evaded and inflammation is out of control because all the PAMPs from the virus, all the dams created by cell damage, they are triggering inflammation, and the antiviral state is not being induced effectively. Now, one of the mechanisms of this protection from the antiviral state is the fact that the virus has proteins that induce the budding out of membrane vesicular structures from the endoplasmic reticulum, and the viral RNA actually replicates within these vesicular structures hidden from the host sensors like MDA5 and RIG-I. So the virus also makes a very specialized protein, which this is NSP3, which is going to make a pore in those ER membranes to allow the viral RNA to come out when it's time for the virus to be packaged and exported. So just to remind you, there are two major sensors in the cytosol, MDA5 and RIG-I. And in short, it's important for us that we recognize structures that lack a cap. And the particular structures on the cap, including the 5' triphosphate, needs to be covered up in order for us not to recognize by RIG-I. So messenger RNAs will not be seen by RIG-I. And then in the cap, there's a 2' O-methyl ribose, which is also important to block MDA5. And what the virus does is that it has enzymes which are going to, so these particular proteins, which are going to make this 7-methylguanosine cap for the viral RNA, and they're going to add this 2' O-methyl group of the cap structure so that the viral RNA will now evade innate immunity in the host in part. So in a very broad sense, what happens in people who have an mild infection or an asymptomatic infection? So in general, we think that these are people with relatively small viral inoculums. They're not people who are prone to severe disease. We can discuss that. Infected cells themselves will not make type 1 interferons because of all the mechanisms that, I haven't covered them all, but we know what they are in general. But the plasmacytoid dendritic cells of the innate immune system, they are going to respond to the virus. TLRs in the endosomes of these PDCs are going to make type 1 interferon. So for someone with very mild disease, even though the infected cells are not making type 1 interferons, PDCs are functional, and this is what will offer some degree of protection. And this is important, but this is going to be bypassed in severe disease. So overall, you can think that if you have very mild disease or asymptomatic disease, the antiviral state is being favored over inflammation. Now, why do some people get severe COVID? And I think this is an interesting question to ask in India in a molecular sense. The most interesting story here has come from Jean-Laurent Casanova, who showed, and in the original papers he published last year, he showed that about 5% of people who get severe disease, not with mild disease, only with severe disease. These are the ICU type patients that were mentioned by Professor Raj. These patients often have defects in the type 1 interferon pathway or in the response to type 1 interferons. And these are minor genetic defects, which are now gradually one by one are being shown to be sufficiently dysfunctional to reduce the amount of type 1 interferon made. More interestingly, he showed that about 10% of people, and he set a very high cutoff, about 10% of people had autoantibodies against type 1 interferons. And this is again, these autoantibodies increase with age. They increase in men and not in women. And the numbers now have gone way up from 10% to closer to about 40%. So there are a lot of people with severe disease are going to be, this disease is going to be explained by an underlying defect in type 1 interferons. Now, I think those of you who are working in India and trying to wonder, why is it that disease is often not that severe? And how does the microbiome work? What does it do? I think you need to think in terms of breaking of tolerance against type 1 interferons as being one possible mechanistic way to think about the question. Now, the other thing that we have shown, so some time ago, Ilka Netravali in my lab had shown that PDCs are actually more lymphoid-like, and this is confirmed by others. And what we showed sometime last year was that when you look at severe COVID, you have a reduction in PDCs, you have a reduction in NK cells, you have a reduction in the earliest B cells as well, and some CD4 T cells. And this I'm showing you the B cell data over here, that you can see that in severe COVID, your transitional B cells, the cells that come out of the bone marrow, are markedly reduced. So that in COVID, as you get severe disease, as inflammation increases, you are reducing the very cells that can help protect you against viruses and help you with the antiviral state. So this compounds the problem and disease gets worse. So from a very broad picture, before I get into some of the data from our own lab, the big picture view would be that in COVID-19, you have increased inflammation and a diminished antiviral state. This is in severe disease. You actually have an increase in myeloid cells in absolute numbers and a decrease in lymphoid cells. So the lymphoid cells that can protect you are decreased. There's an increase in pro-inflammatory cytokines like IL-16 and alpha and chemokines as well. But there's a decrease in type 1 interferons. And then we have activation of complement, we have netosis, we have coagulation, all of this is increased. When, as a consequence of all of this, we are losing tissue integrity and organ function. And it is this innate immune imbalance, which, as I'm going to tell you, can be influenced by adaptive immunity, is what is really driving severe COVID. Now, how does the disease impact adaptive immunity? And I think the lessons coming out of Manaus and places in Brazil, again referred to by the previous speakers, let us hope this does not play out in India, because what I'm going to suggest to you is that adaptive immunity can provide you protection maybe for some months. And if you read the SARS literature well, you start to understand why, but we are giving you mechanisms. And once that wears out, you are going to have the development of more variants, because adaptive immunity that is generated naturally is not strong enough and is not diverse enough, is not potent enough to control the generation of variants. And perhaps that is the reason why in places like Brazil, we now see the reemergence of disease many, many months after they thought that they were doing quite well. So let's see this mechanistically, just to remind you that during the immune response, T cells help B cells to form germinal centers. And germinal centers are these Darwinian structures where you have the genetic diversification of B cells, so that you have receptors. The original receptor is now diversified to give you many different somatic mutations of the antigen binding sites. And then the highest affinity B cells get selected, and these, some of them early on may become memory B cells, though we think that memory B cells can come from outside the germinal center as well. But in the germinal center, with many rounds of selection, you're going to get high affinity plasma cells. And these high affinity plasma cells are then going to be homing to the bone marrow and will make antibodies for life. Okay? And what we saw happens in severe COVID-19 is that if you look at a control, now we're looking at thoracic lymph nodes, and in a control, and these are age-matched individuals who happen to pass away in our hospitals at the same time. And there is a microbiome, as you can recognize, there's a lung microbiome. And this is causing the formation normally of germinal centers. And you can see beautiful germinal centers using BCL6 staining in the controls. And these have withered away in patients. And when we first published this was just with a small number of patients. We've extended our study, so we know this from larger numbers. Essentially, what we're telling you is that germinal centers with BCL6 are very well formed in controls. These are not healthy people, but they are controls. They don't have COVID-19. Whereas in COVID-19, either when you look early in disease, so this is very acute disease, on convalescents, people who are in the ICU for maybe 2 months, you can start to see some return of the BCL6 positive cells, but the numbers are way down, and I'll show you some quantitation in a minute. So there is the loss of germinal centers. So as a result, you can make antibodies. You can make neutralizing antibodies. The neutralizing antibodies are quite potent, but they are not long-lived and they are not diverse. So the ability to handle something a little different isn't great. The same is true of the memory. So just quantitation. So we are able to do tissue quantitation, go to multiple colors. and look at things and look for cell-cell interactions. We use registration, so you can go back and look at the same tissue with multiple new stains, looking at the same nucleoli in cells. So it's perfect registration. So essentially, B cell numbers are down, T cell numbers are down. This is in COVID patients. CD19 positive, BCL6 positive cells. These are your germinal center B cells. These are down. You should note that we are looking at absolute numbers. We are quantitating per square millimeter and also looking at the proportion. AID positive cells, this may be a nuance for many of you. AID is induced by T cell activating B cells. It is responsible for both class switching as well as for somatic hypermutation. So this is to say that AID is not gone. T cells are still activating B cells. It's just that you can't make the germinal center. Okay? And now this is to tell you why you can't make the germinal center is because we are losing a specialized type of T helper cell. And I'll tell you the reason why we think we're losing this, but this T helper cell is being lost, the T follicular cell that expresses BCL6. So just to show you CD4, CXCR5 positive cells, these are T follicular helper cells. BCL6 is the transcription factor here that defines the T follicular helper cell as well as the germinal center B cell. And these cells, I'm going to show you quantitatively, are markedly reduced in COVID-19. You can see what I'm pointing to here. So again, this is quantitation using different measures. So somebody like Amit in the audience will follow this, I'm sure, in more detail. So just take my word for it. We use different markers for TFH cells. These T follicular helper cells, they are markedly reduced in COVID-19. We are looking in lymph nodes, remember. We're looking at lymph nodes, the thoracic draining, thoracic lymph nodes in severe COVID-19. And you can see the reduction with BCL6 positive cells. And when we looked at the spleen as well, so we have from patients matching lung, spleen, and lymph nodes, and more as well. This is a remarkable operation by my close collaborator, Bobby Pedera at the Brigham, where autopsies were performed with tremendous rapidity so that we can have preserved tissues. And we have even got to the point of doing flow cytometry and single cell RNA-seq on these tissues. It's possible to do it with lymph nodes. It's harder to do it with spleen and lungs for the other techniques. Okay, but what I'm showing you is we fix the lymph nodes, we fix the lungs, and we look at everything very quickly. This is just to tell you that the transitional B cells decline with disease severity. This says that, cells, when you get severe viral infection of any sort, you are going to see lymphopenia. And if you ask me what the mechanism is, I'll tell you, but there is lymphopenia. Okay. When you look at expanded, activated disease-related B cells, again, this increases with disease severity. So these are various populations we look at, which may or may not be familiar to some of you. Like these are populations most of you don't think about, but these are all going up in disease. They go up with disease severity. And then we even ask, are these antigen specific? So we use probes for the RBD. So we now use spike probes, but at that time we use probes for the RBD. So by flow cytometry, we're looking at RBD specific cells and then using our 26 color flow panels to see which populations they fall in. And basically we show that these activated cells are specific for SARS-CoV-2. Okay, this is in the blood. I was showing you data much earlier on from the tissues, but both the tissues and the blood correlate. So the big picture view was, if you were to get measles or mumps, or if you got a yellow fever vaccination, what is going to happen is you're going to have nice TB collaboration. You're going to form T follicular helper cells with BCL6, and you'll form germinal centers. And as a result, your yellow fever vaccine will give you antibodies for 100 years. Okay, so there's going to be really long-lived immune responses. If you had got SARS or MERS or Ebola, or if you got COVID-19, okay, and I'm extrapolating based on some other pieces of data, the most detailed studies are studies in COVID-19. In all those contexts, you got a lot of Th1 cells, and then I'm going to show you a lot of cytotoxic CD4 cells. There's a block in BCL6 positive germinal center TFH differentiation. Primarily, we think because driven by certain cytokines, you are causing a deviation of your differentiation away from these cells towards another cell type, okay? As a result, as this block in BCL6 positive germinal center TFH differentiation, you fail to make germinal centers. You have B cells, you have follicles, but you don't have germinal centers. As a result, your antibodies are going to be relatively short-lived. In about 10 to 15% of patients, we predict you will get long-lived antibodies. Those are patients who recovered after severe disease and then made germinal centers when there was still virus around. In the vast majority, it's going to be like SARS, where again, in the vast majority of SARS patients, antibodies declined after a year and a half when you looked at them. In fact, in SARS, if you looked after 5 or 6 years, you didn't even find memory B cells or memory CD4 T cells. Now, so what is happening in the lungs? What's causing this disease in the lungs? Why are we getting severe disease in the lungs? Is it only innate immunity, or is there a role for adaptive immunity? Why do we get fibrosis? Why is there severe fibrosis later in the disease? So I'm going to argue that immune deviation away from this BCL6 T follicular helper cell subset is driving you towards a T cell subset that drives you to cytotoxicity, which might help you clear the virus, because you do clear the virus, and also cause fibrosis. And this is probably microbiome influence, and I'll come back to that at the end. Now, so this is just saying, if you looked in the lungs, there's an increase in netosis, there's an increase in neutrophils. We look at all of this. Since no one else has studied the lung in any detail, we had the opportunity, we looked at the lung. So we're looking at citrullinated histone H3 for netosis. You can see a lot more in COVID. We're looking at macrophages, but what I'm not showing you here, we also look for ASK1 to show you that inflammasome is activated. It goes up in COVID. We looked at NK cells, not expanded, ILC1s, not expanded, ILCs, not expanded in the lung. So these are innate lymphoid cells. This is just to tell you that innate immunity doesn't seem to be doing the job in terms of clearing the virus. Lung CD8 cells, this has been reported in the blood and in BALs by others, but lung CD8 cells have what is consistent with a exhausted phenotype. There's a lot of PD1 positive, CD8 positive cells. The lung is filled with a lot of PDL1, and the lung also has a lot of IL-27, which again, Amit might find interesting because my friend Vijay Kuchru has been trying to argue this, and most people are not listening to him about the possible role of IL-27 in exhaustion. Okay, but our data is consistent with that. There's an expansion of certain T cells in the lung. So we are now looking at CD4, SLAMF7. Sorry, these are markers we use. We also use CX3CR1. We also use granzyme B. And these are cells we call CD4 cytotoxic T cells. And CD4 cytotoxic T cells are increased in the lung. And as you look at disease, as you go late, the numbers go up. It's one of the significant cell numbers that increases in severe COVID. So CD8 T cell exhaustion has likely evolved to protect us from organ loss and death. You don't want your liver being wiped out by hepatitis or, in any severe viral infection. Exhaustion allows us to slow down killing and allows us to slow down our organs being destroyed. But this does come at the price of some viral persistence. So we think CD4 CTLs, first of all, they can only target cells that have both been infected and have also been induced to express HLA class 2. Okay, so this will ensure that killing is not precipitous, it is slower. And there's growing evidence now that CD4 CTLs participate in viral clearance. So in resolving COVID-19, we are seeing that the numbers of these reactivated granzyme B expressing CD4 CTLs and the numbers of granzyme B expressing CD8 T cells, so this is a sign that they got reactivated, is roughly equivalent. So in non-COVID, of course, we don't see these CD4 CTLs, but we do see that there's about equivalent numbers late of CD4 CTLs and CD8 CTLs. So at this point, late in disease, virus has been completely cleared. We can't find virus. So we think this is in part because of the cooperation between CD4 CTLs and partly exhausted CD8 T cells. So the big picture view for us for the pathogenesis of COVID-19 is that you start with this defective antiviral state. You have a lot of inflammation, inflammasome activation, netosis, cytokine storm. You activate naive CD4s and CD8s in your lymph nodes. Most of your CD8 T cells are exhausted. You don't make T follicular helper cells, but you make a lot of CD4 CTLs, and this happens more late. And the CD4 CTLs go into the lung. There's a lot of HLA class 2 being expressed, which I'll show you in a minute, on your epithelial and endothelial cells, and there's fibrosis. And so we think CD4 CTLs, maybe exhausted CD8 cells, are contributing to the fibrosis, as we have shown in other diseases, and I'll come back to that in a minute. And that this will correlate with increased apoptosis of target cells and cause viral depletion. Okay? So let me just skip this. There's a late surge in CD4 CTLs correlates with an increase in lung apoptosis, and likely there's a collaboration with exhausted CD8 T cells. So this is just to show you that there's a lot of TB collaboration. So what we are arguing, and we can discuss this if there's any interest, that when B cells help some T cells to become TFH cells, but in the case of severe viral infection, they're deviated, they express different proteins on their surface, and they're now inducing these T helper cells to become cytotoxic CD4 T cells. So we have evolved this approach where we cause the induction of cytotoxic CD4 T cells to occur in severe viral infections and in other severe infections which are non-viral. Now, what about, I said there was HLA class 2. So you looked at endothelium. So you're looking at CD31 for endothelial cells. You can see HLA-DR. This is class 2 being induced. You can see the CD4 cells sitting on this endothelium. It doesn't prove anything, just says this is possible. Same thing we are seeing for epithelium. Again, I'm focusing on an area where you can see a CD4 T cell kissing an epithelial cell. The epithelial cell also expresses HLA-DR. And if you look at just the frequency, now keep in mind our controls have disease. These are not non-disease people. They just don't have COVID-19. But we see an increase in these class 2 expressing cells with inflammation, which is to be expected. But that gives you a target for a CD4 CTL. Now we looked for apoptosis by looking for cleaved caspase 3, and we're looking for cleaved caspase. Most of the cleaved caspase 3 is actually in epithelial cells, and we can see an increase in cleaved caspase 3 late in disease. So there's an increased apoptotic death with the increase in CD4 CTLs. And then, of course, this total distortion of the lung, as has been described by others as well. It's just we use more colors, it looks nice. We looked in the blood. So we have been studying a cohort with, over 70 severe COVID patients in it. But this just to tell you, overall, the one T cell subset in the blood that actually significantly goes up in severe disease compared to convalescent patients is CD4 CTLs. And CD4 CTLs, this is looking at C-reactive protein levels and comparing it with CD4 CTLs. And you can see a nice movement towards an increase in CD4 CTLs with more severe disease. So CD4 CTLs are likely controllers of viral spread, as has been shown by others in dengue and some people in CMV. Likely requires activated B cells regeneration. I'm not going to go into this. We are doing a lot of studies in the mouse to try to understand the mechanism. They come to the fore in the context of inflammation and CD8 T cell exhaustion. They're known to secrete. We actually showed this. They secrete IL-1 beta and TGF beta, and this is shown many years ago by Hamid Matu in our lab. And they are likely inducers of fibrosis and exacerbation of inflammation in COVID-19. They're a potential therapeutic target in COVID-19 and in what has been called long COVID, or which we now call the post-acute sequelae of COVID-19. So every protective immune mechanism can also drive disease. We all know this. It's true in medicine. Anything that we use for protection, we can then cause it to also cause an imbalance. So CD4 CTLs are a dominant tissue infiltrating T cell subset in 4 human fibrotic diseases. We've described 3 of them. So we showed this in IgG4-related disease. Last year, we had a JCI paper showing this for systemic sclerosis. We just published a paper on fibrosing mediastinitis, which is a fibrotic disease caused by Histoplasma capsulatum. And there's a paper that's just come out from another group showing that the orbital myopathy of Graves' disease, they use single cell RNA-seq to show that you have the dominant T cells here are CD4-CTL. We also just published a paper in collaboration with Ramnik Xavier that in IgG4-related disease and systemic sclerosis, there's a clear microbiome connection. In fact, there's like a microbiome signature we are thinking of in severe fibrotic diseases. So there was a lot of metagenomic analyses, and I can get into this if you have questions. We think that CD4-CTLs, in conjunction with specific drivers of the microbiome, may be drivers or some of the drivers of post-acute sequelae of COVID-19. Some people will call this long COVID. And there's the connection, therefore. I think we learn from microbes and we understand common diseases by trying to see how they interact with the immune system. And this is the broad scenario. I think you have injury and apoptosis of some epithelial cell driven maybe by CD4-CTLs. When the rate of cell loss exceeds the rate of replenishment, there's space, and the space is filled by activated fibroblasts and myofibroblasts that deposit collagen, and then we call this fibrosis. Okay. So just an overview, SARS-CoV-2 evades RNA sensors. The type 1 interferon response is defective. Viral PAMPs and an overdose of DAMPs probably drives inflammation. You have inflammasome activation, neutrophil activation, netosis. There are other contributors. There's underlying susceptibility to inflammasome activation. This could be metabolic syndrome, the genetic drivers, defects in the type 1 interferon pathway, pre-existing antibodies, type 1 interferons. There's a high level of inflammation in draining lymph nodes, which reduces effective germinal center formation. It induces extrafollicular activated B cells. I didn't talk much about them. And it fosters CD4-CTL differentiation. In the lungs, HLA class II expression is induced. CD8 T cells look exhausted, but CD4-CTLs expand. They link to increased apoptosis, viral clearance, and lung fibrosis. Okay, a lot of people in my lab have been involved in this work. I should just mention a few. Jocelyn Farmer, Vinay Mahajan, he's a product of All India Institute, Cory Perugino, Hang Liu, and more recently, Tong Shu and Daniel DeToro, one of the MD PhD Path Fellows in the lab. But most of the tissue work was driven by Naoki Kaneko. And wonderful collaborators, in particular, Robert Padera at the Brigham, who heads the autopsy service there, Shu Yu at the Reagan Institute, who helped us collect all the blood samples, and is a wonderful collaborator, Bruce Walker, who organized the effort in Boston to collect all these samples. So all the people in my lab, not all the people, many of them during the shutdown were actually working on sample collection. And then the collaborators who have given us very important probes at the Reagan Institute, Aaron Schmidt, who supplied the world with the spike protein starting from January, and helped us, of course, with all the probes we use for picking up antibodies. I didn't talk about the work with Gaurav. We've been looking with him at T cells that are antigen specific in COVID-19. And Julie and Shaoxuan and Jocelyn were the key drivers of the earlier B cell work, along with Naoki Kaneko. And I can stop sharing now, and I'm happy to take questions if there's time. I should tell you that this is my first talk to a live audience in a year. I've been teaching and talking to people, but the audiences are not live. They are sitting at their computers.
There are actually, Shiv, there are people here sitting in the audience also.
I know, I saw that.
So Amit is sitting there. So,
I saw him actually.
Okay. And if you remember, when you were heading that research unit, when Dr. Jalan's institute in
I remember you coming to Calcutta at that time.
Yeah, so
আমি তো কলকাতায় ছিলাম তখন।
Okay. So it was a great pleasure. Why you used to invite me in your research council. So I thought it took me some time to recognize you, but your smile is the same. So
my head is different.
So there are questions which we will pass on to you. And if you could please answer them, because this
Okay, they'll be in the chat.
hybrid session. So please pass on the chat, Nirja, to Dr. Sipille.
Yeah, so far I don't see anything in the chat.
No, you will start getting it. Who is passing this on?
I want to ask a question.
Okay, Dr. Panda. Dr. Panda, who is the Director of National Institute Immunology, he has got a question. Dr. Panda, come here.
Good evening, sir. Nice talk. I had one question. You said there is a severe defect in BCL6 positive TFH cell and germinal center. So my speculation or my question is, anything, either a adjuvant or an excipient in vaccine, which will improve BCL6 positive TFH cell or germinal center, will be useful for memory?
Yeah, so I should tell you, we have been looking at vaccinated individuals. And the first thing that is heartening, at least so far, we have looked only at the 2 mRNA vaccines, but we have now started to collect data from the J&J vaccine, but it's too early for us to give you any answer. But for the mRNA vaccines, all the signs are of, first of all, the antibody titers are about 15-fold higher than natural infection. You can expect to get very good neutralization because of that. There is every sign of memory and every sign because of the somatic mutation rate. So you look at the somatic hypermutation rate, you can gauge whether or not you're coming out of a germinal center. And so there are antibodies that are coming out of germinal centers. There is actually published work already from Drew Weissman on mRNA vaccines in animal models, which already established the actual formation of germinal centers. So I think the data is all very good now to say that the vaccines are going to protect us. And they, as you know, they already protect against variants as well, if you get a high enough titer. So you do need to get a good vaccination. Keep in mind that some vaccines will not give you, so, vaccines that have these kind of adjuvants, like the mRNA vaccines, are definitely going to give you maybe the higher levels and the somatic hypermutation levels. It may not be equal for all vaccines.
Okay. Thank you, sir.
Sure.
Dr. Pillai, I also have a question that there are two things which I was very intrigued upon and learned was the special population of CD4 CTLs, which you measure in the lungs. And these CD4 CTLs, you said have a express enzyme and also they are selected for spike protein.
So Pandurangan Vijayanand, I don't know if you know him, he published a paper in November in Cell using single cell RNA-seq. And essentially he showed that the antigen-specific cells in the blood were CD4 CTLs. So he and I have been working on CD4 CTLs in different ways. He looked in the blood. We have looked in the blood using his approach, and we find that they're also spike-specific. But what we have done is to show that they're in the lymph nodes and in the lung as well. So that it's not just a blood finding. These are antigen-specific cells as shown in the blood. In the lung, we can't show it's antigen-specific. It is too hard for us in a section to show that. But in the blood, they are antigen-specific, spike-specific. Not spike only, right? We have used antigenic peptides from SARS-CoV-2.
Okay. And why do you think this particular discordance is there? Because many of the viral infections, these are the CD8 cells which are measured to ultimately look at protective immunity. And why it doesn't happen in SARS? You said that these cell population are more harmful than beneficial, but it is a discordance in viral infections. We measure that. Even in HIV, we measure that as one of the parameters.
Okay, so let me just give you a little context. So in HIV, Hendrik Streeck and Bruce Walker published a paper about maybe 10, 12, 15 years ago, showing that in the first year of disease, the levels of CD4 CTLs are inversely correlated with viral load. So they certainly protect even in HIV early on. But then you destroy CD4-CTLs with the viral infection. CD4-CTLs, I personally think, are a very important part of antiviral protection. In our textbooks, we still don't highlight them. I mean, I'm responsible in part for that because we're being cautious. So in the textbooks, we still say CD8-CTLs. But if you actually go and look at human patients and you look at people who have CD8 defects, genetic defects in CD8s, they have very mild viral infections. You look at people who are basically SCIDs, you have severe viral infections. So I do think there is a role, protective role, for both CD4-CTLs and CD8-CTLs against viruses in certain contexts, severe viral infections. Of course, everything that is helpful can also be linked to disease. Fibrosis is also something that is wound healing gone awry. So I think sometimes these things do happen. We have linked them to disease, but I think they're protective as well as disease causing.
And you will now have some information over there in the chat. But the PDL1 which you measured there, how did you correlate it with the immune responses in COVID?
So PDL1 is actually found in any inflamed lung. So it's not like it's very specific for COVID. So we were more concerned to say that, okay, you're finding PD1, but is the ligand there or not there? If the ligand is not there, the PD1 means nothing. There's actually a lot of the ligand. That's all we find as a correlation. So let me just look at the questions in the chat. One is not a question. This is something about COVID. I'm sorry to hear about somebody whose husband passed away. Yeah, so I mean, I think what she's describing is that her husband had had mild COVID, got admitted, but then he was intubated for some reason, and even with mild infection, which is odd. But then the blood cultures, he got infection, and the blood culture was not sensitive. This is because of maybe intubation tube. Severity of disease is related to the mutation of some kind. In some people, the severity of disease is linked to pre-existing variants in the type 1 interferon pathway linked to toll-like receptors. Do antioxidants really help against COVID-19? I mean, I presume they might. I don't think there's any hard enough data for me to say that. Even with, like vitamin D3, we hope it helps, but the data is a little difficult to be 100% sure about. How much is the trained immunity and gut microbiome related? This is a very interesting question. I mean, I hope that it is trained immunity in India that is protecting people, but I'm hesitant to say that after seeing what has happened in South Africa and Brazil. I would wait. I hope it is so. I hope it's trained immunity. And how much is the gut microbiome related, and how much is that related to other infections like TB? I don't know. Obviously, these are things you should be studying. Are those all the questions, or are there any more questions? Oh, is there any cytokine profile that seems to prevent the development of germ center? Yes. So in certain animal model studies, and this is what we extended to humans, so there's a severe model of malaria. There's a model which Dan Baruch, my colleague, and Rafi Ahmed developed using LCMV in the mouse with a additional twist, which if you want, I'll tell you about. And there's yet another model of a rickettsial disease, severe rickettsial disease. In all of these diseases, you lose germinal centers. However, if you then go and block TNF, the germinal centers can come back. So basically, the milieu in the lymph node of having excessive TNF, and we published this in our paper last year, that excessive TNF might be driving the immune deviation.
The immune deviation happens in those people who are suffering from severe COVID, as far as I can understand.
Yes.
So, Sanal, 1 minute. This is a question from Dr. Sanal, who came to India from Albert Einstein. And so, Sanal, go ahead.
Yeah, yes, sir. So in these people who finally, suppose a fraction of these people will recover from severe COVID. So these people have a lifelong, means a longer immunity after the recovery or not, compared to those people who are vaccinated?
Yeah. So I actually think that the 10 to 15% of people roughly, it's not an accurate number, who get severe COVID, who recover, who still have virus, because the virus tends to persist in the gut a little bit, they can still form germinal centers. And my friend Patrick Wilson actually showed that a small number of people are making, we're inferring germinal center in them, right? We're not doing biopsies. This is from the somatic hypermutation rate of the plasmablast that you can see in the disease. So yes, I do think that in some people, if they recover, they will actually have pretty good immunity. They may never need vaccination. It's hard to identify them because these are very difficult tests to do for an average laboratory. So I think those people will just get vaccinated and they will just get one dose, and that's how it will work. It's probably not going to be harmful to do that. But yes, I completely agree that a small percentage of people who recover will probably have pretty good immunity. The majority will not. That's what we saw. If you look at the SARS data, which has been studied without maybe this level of granularity, that's the story that came out.
So we have a question from Amit to you. So Amit, say hello to him because he mentioned you several times.
Can you hear me?
Hello,
here?
Amit. I can't hear you very well yet.
Okay. Hi, Shiv.
Yeah, no. Hi.
Good
I'm
to
good. Why are you so dressed up, Amit?
This is actually in a year I got a chance to come out and in a kind of talk. Yeah. So thank you. It is always a pleasure to actually listen to your talk, and it's a great work, your cell paper. So the question, what I'm trying to ask you is, recently there are 3-4 reports are coming. One is about IL-6, clinical trial is showing some good data. Recently the role of GM-CSF has been shown in science immunology. So they are kind of indicating towards the role of Th17 cells, because Th17 cells produce GM-CSF, and IL-6 is one of the driver to generate Th17 cells. So I'm wondering whether in your acute patient in autopsy, whether you have seen some difference in case of Th17 cells elevated or not.
Yeah. So Amit, we look carefully. There is some increase in Th1 and Th17 cells. Okay. It's not striking, but it is there. In blood studies, you probably know this better than me. If you look carefully at all the COVID, there are a lot of good COVID blood studies. There's not a standout response from Th17 so far, but it's there. So obviously, when you have inflammation, you are going to have Th1, Th17. Keeping in mind, I think if you think about the IL-6, and this could also be the GM-CSF, I think earlier on, a lot of what's happening in COVID is innate. So the only other paper that has looked at the lung in any detail is that from David Ting that came out, I think it's Nature Com a month or so ago. And in that paper, I mean, they didn't have the approach to look at various T cell subsets, but the numbers of T cells is low. And I agree that early in disease, if you look in the first acute phase, when they're very sick, if you actually quantitate T cells, they are very low. There's lymphopenia, there's not that many T cells. So I think a lot of the initial disease is driven by innate immunity. And that even without T cells jumping in, you have so much damp creation by so many cells being damaged and dying that you are activating inflammation, and the T cell has not yet come into the picture. So I do think they could be important, but I do think IL-6 can be produced without Th17 cells, as you know. I mean, and if you have very severe activation of innate immunity, you might get enough Th17 cells. We were intrigued to know whether there was a possibility of maybe, ILC3s and all of that. Maybe they're important. I don't know, but the numbers are not great.
So thank you, Shiv. It has been great pleasure to have you with us. We will be very, very grateful. We publish a proceeding, which is ISBN level. We will be grateful to receive your paper. Whatever you want to delete, which is unpublished, you are welcome, but we will greatly appreciate it. And we will be sending you our token of appreciation through one of the couriers. Thank you so much for being with us.
Well, thank you all. Thank you for listening. Bye-bye.
Well, thanks to Professor. So now it's time for felicitation process. Now I would like to request Professor Ganguly to kindly felicitate our esteemed dignitaries. So requesting Professor Ganguly to felicitate Professor V Samuel Raj. I want everybody should applause. Everybody please put your hands together. Now may I request Professor Ganguly to kindly felicitate Professor Anil Kumar Srivastava. Everybody please put your hands together. Requesting sir to kindly felicitate Dr. Amulya Panda. Everybody please put your hands together. Now to Dr. M.S. Chauhan. Everybody please put your hands together. So may I request Professor Anil Kumar Srivastav to kindly felicitate Professor Nirmal Kumar Ganguly. Everybody please put your hands together. Thank you so much. So ladies and gentlemen, we have to proceed further. We have to take this symposium further. So now I have the pleasure of inviting the chairperson. But before that, I would request everybody to kindly take your seats. Requesting all the esteemed dignitaries to kindly take your seats. And now we are proceeding further. So ladies and gentlemen, may I have the pleasure of inviting Chairperson Professor Amulya K. Panda and the co-chairperson Dr. Amit Avasti for presiding over this scientific session. Professor Amulya K. Panda is a scientist at National Institute of Immunology, New Delhi for last 30 years. Currently, he is the director of NII. He has master degree in chemical engineering from IIT Madras and a PhD in biochemical engineering and biotechnology from IIT Delhi. His research interest includes bioprocess engineering, recombinant fermentation process development, high throughput protein refolding from inclusion bodies and vaccine delivery using biodegradable polymer particles. He has published more than 145 research papers, 12 book chapters, and an inventor of more than 35 issued or pending patents. He is a fellow of Royal Society of Chemistry, Cambridge, fellow of American Institute of Chemical Engineer, and fellow of National Academy of Microbiological Sciences, India. Dr. Panda is instrumental in initiating immunoengineering program at NII. Everybody, please put your hands together. Keeping the decorum, I request all of you to kindly be seated. Requesting once again, kindly be seated. Also, I would like to request Dr. Amit Avasti. He has significant contribution in understanding the biology of helper T cell subsets in tissue inflammation in autoimmune diseases, allergic inflammation and infections. He identified the transcriptional signature of pathogenic and non-pathogenic Th17 cells and TR1 cells. Dr. Amit has contributed significantly in COVID-19 pandemic by establishing the animal models to study SARS-CoV-2 infection. Using the animal models he has supported vaccine research and drug discovery for COVID-19. So requesting Professor Panda and Dr. Avasti to kindly take this session forward and introduce the speakers. Thank you, sir.
Is he online? Is the speaker online? Kenji Oishi? Is he there?
Yes, yes.
Okay. Good evening, everybody. At the outset, I'd like to thank Professor Ganguly for giving this opportunity. We'll go with the session, which we have three speakers. And as the organizer told me and Amit will be going through this. And let me introduce the past speaker. He is Dr. Kenji Oishi. He has his PhD from Tokyo University of Pharmacy and Life Sciences. Dr. Oishi is currently the Associated Researcher at Microbial Research Department in Yakult Central Institute. His major research topic is dynamics and functioning of gut microbes, including probiotic. He has belonged to the Yakult Hunter Foundation, European Research Center of Microbiology in Belgium for last 10 years, and was involved in a number of clinical trials on physiological effect of probiotic as the science director. He has published 17 research papers and a review article. In fact, considering this is the probiotic symposium, and I think everybody know about Yakult, it could not have been better than anybody but Dr. Oishi to give a talk on dynamics of probiotic strain in small intestinal tract. I'll invite now Professor Dr. Oishi to deliver his talk.
Hello. Hello.
Hello, you can share your presentation.
Can you hear me?
Yes, you
Okay.
loud and
Okay.
clear.
Okay, thank you. Thank you, Professor Panda, for your very kind introduction. It's a great honor for me to have this opportunity to make the presentation. It was supposed to be my first trip to India, but now I'm participating in this symposium from Tokyo, Japan. It's a disappointing, but looking forward to the next opportunity. Tonight, I try to communicate with you via this web conference. So I will share the slides. All right. Can you see the slides? Well, the topic I'm going to address today is the dynamics of probiotic strains in human small intestinal tract. My today's talk includes the following three topics. To begin with, I will give you an overview of probiotics, and then I will introduce our latest finding by showing the data about dynamics of probiotic strains in human small intestines after an ingestion of commercially available fermented milk products. Thereafter, based on the findings, I will present a hypothesis about host stimulation by probiotics. Okay. First, I'm going to give you an overview of probiotics. Probiotics, which include lactic acid bacteria and bifidobacteria, have been marketed in various forms, such as fermented milk, tablets, biscuits, and chocolates. The Food and Agriculture Organization, FAO, and World Health Organization, WHO, defined probiotics as live microorganisms which, when administered in adequate amounts, confer a health benefit on the host. The International Life Science Institute has a similar definition, or probiotic are live microbial food ingredient that when ingested in sufficient quantities confers health benefits on the consumer. As is clear from these definitions, probiotics must be alive and have beneficial effects on the host. As shown in this table, in terms of to be alive, in order to examine the ability of probiotics to reach the intestines in a viable state, the recovery of orally ingested strains in human specimen has been investigated in several studies. For example, it has been demonstrated by cultivation of feces that B. breve Yakult, BBRY, can be recovered in a viable state from the feces of subjects. After ingestion of a fermented milk containing this strain, LKSAI sirota, LCS, has been confirmed to survive in the feces of subjects who consumed a fermented milk containing this strain in several regions, including Japan, Asia, and Oceania. L-para-KSAI B21060 and L-lamnosus GG, LGG, were also reported to be survived in colonic biopsy. Thus, it has been confirmed that ingested probiotics can reach the colon and feces. However, reports showing the behavior of ingested probiotics within the intestinal tract have been limited. In terms of benefit to the host, probiotics have been shown in numerous human and animal studies to improve gastrointestinal symptoms, bowel habits, constipation, host defense against infection, immunological control, cancer prevention, stress-associated symptoms, and sleep. As shown in this slide, concerning the immune control, the function of probiotics varies between the strains. Some strains show immune stimulating effects to augment the immune defense against infection and cancer. For example, exopolysaccharides of L-Delbecki subspecies vulgaricus or LL1073R1 augment natural killer cell activity and induce interferon gamma production through phagocyte regulation. On the other hand, some other strains show anti-inflammatory effects to control inflammatory responses, resulting in alleviating the symptoms of inflammatory bowel disease, IBD. For example, E. coli Nisu 1917 induces decrease of pro-inflammatory cytokines such as IL-2 and TNF-alpha, and increase anti-inflammatory cytokines through the stimulation of human dendritic cells by their specific lipopolysaccharides, LPS. LCS is quite unique. Interestingly, this strain has been reported to have two different active components, rigid cell walls, which act as immune stimulating agent, and PSPG1, which act as an anti-inflammatory agent. The rigid cell wall of LCS is associated with IL-12 induction in the murine macrophages. The IL-12 production induced by LCS was positively correlated with the enhancement of NK cell activity, and this effect was diminished when treated with anti-IL-12 monoclonal antibody. On the other hand, PSPG1, a specific cell wall component of LCS, works to inhibit IL-6 production in LPS-stimulated lamina-propria dendritic cells isolated from the murine model of IBD. LCS prevented the development of sodium dextrosulfate-induced colon cancer in mice through suppressing IL-6 mRNA expression on dendritic cells in the colonic mucosa, and the effect disappeared in its mutant strain deficient in PSPG1. The balance between these two different features of LCS, immune stimulating effects and anti-inflammatory effects, is thought to be flexibly altered depending on the conditions of the host immune system. Next, let's look at the modulation of brain function by probiotics. Accumulating evidence suggests that multiple routes are involved in the action of probiotics on brain function via the gut-brain axis. It has been suggested that microbial cellular components and metabolites of the complex gut microbiota may influence brain functions via blood circulation, immune system, humoral pathways, as well as neuronal pathways. And differences in microbial diversity and taxonomic composition have been observed between stressed individuals and controlled individuals. Thus, probiotics, beneficial to humans, should help to maintain homeostasis of the neuroendocrine and immune systems by preventing a disturbance of the gut microbiota. Regarding the shift in gut microbiota diversity, in a human study of medical students under academic examination stress, LCS suppressed stress-related reduction of the alpha diversity index of the gut microbiota. Daily intake of L-gasseri CP2305 increases alpha diversity of the gut microbiota and prevents the stress-induced decline of bifidobacterium. Shifts in gut microbiota diversity have been associated with mental health and psychiatric disorders such as stress, sociability, cognitive function, anxiety, depression, and autism. Therefore, the alpha diversity index may be a potential marker of the association between the gut microbiota and psychological changes. Neuroactive metabolites of the microbiota, butyrate, maintains brain-derived neurotrophic factor levels and neurogenesis in the hippocampus and improves depression-like behavior. The butyrate producing bacterium, Clostridium butyricum, nearly 588, CBM 588, has been effective against depressive symptoms when used in combination with antidepressant. Recent findings indicate that probiotics can induce the excitability of vagal afferents. For example, LCS provokes the activity of the gastric branch of the vagal afferent and suppresses the stress-induced activation of corticotropin-releasing factor expressing cells in the paraventricular nucleus of the hypothalamus. This suppresses stress-induced hypersecretion of glucocorticoids through modulation of the reactivity of the hypothalamic pituitary adrenal axis. Administration of L. brevis SBC 8803 promotes the secretion of serotonin from the small intestine. This is followed by stimulation of activity in the intestinal branch of the vagal afferent and in the stomach's branch of the vagal efferent. These observations suggest that lactobacillus probiotic strains modulate stress-induced activation of the hypothalamic pituitary adrenal axis by acting on the neuroendocrine system. This is a summary of my talk so far. First, I explained that some probiotics had been shown to reach the intestines in a viable state, and then I introduced some beneficial effects of probiotics to the host. On the other hand, what happens to the ingested probiotics between ingestion and excretion in feces and how they exert their physiological effects has been unclear. Therefore, we tried to elucidate the environmental change in the gastrointestinal tract after ingestion of a probiotic product. Next, I'm going to explain our latest findings regarding the dynamics of probiotic strains in human small intestines after an ingestion of fermented milk products. We use the small intestinal fluid perfusion using endoscopic retrograde bowel insertion, ERBI technique. This technique is a powerful tool which allows to collect ileal perfusion fluids periodically. A double lumen tube featuring an occluding balloon was inserted retrograde through the colon and placed at the position approximately 10 centimeters from the ileocecal valve. This made it possible to stop the downstream movement of contents, introducing a perfusion solution through the inner tube and collecting the ileal fluids via outer tube with the contents coming down from higher in the gastrointestinal tract over time under physiological conditions without affecting secretion of gastric juice and bile. This photo shows seen during an ERBI procedure. This is a subject, and this is an endoscope operator. At this moment, he was inserting the double lumen tube retrograde through the colon. After inserting the tube and placing the balloon, the subject was placed supine on the bed, and then the perfusion was started. Buffer was continuously infused through the inner tube, and ileal fluid was continuously aspirated from the outer tube and collected. Subjects ingested test meal that was probiotics fermented milk product within 5 minutes after the start of the perfusion. Here is an overview of the study. Commercially available fermented milk, LFM and BFM, were used as the test mean. Viable LCS and BBRY numbers contained in LFM and BFM were at least 40 billion and 12 billion respectively. Subjects were healthy male university students. All the subjects were requested to consume a low residual food instead of a normal meal on the day before the trial. Suppositories were administered at the night before and in the morning of the trial, but intestinal lavage was not performed. This is a schedule. After the ERBI operation, subjects were ingested test meal, and then buffer was continuously infused through the inner tube, and ileal fluid was continuously aspirated from the outer tube and collected every 30 minutes until a maximum of 7 hours after ingestion of the test meal. From the collected ileal fluid, DNA was extracted and the microbiota composition was analyzed using 16S rRNA gene profiling. Here are the results regarding change in ileal microbiota composition after LFM single ingestion. After the ingestion of LFM alone, LCS was first detected in ileal fluid anyway from 0.5 hour in subject C to 4 hours in subject A. In subject E, streptococcus, this one, occupied about half of the ileal microbiota until 2 hours after LFM ingestion, after which LCS predominated. The relative abundance of LCS in the ileal microbiota peaked above 90%, and subject A and B and C remained high in the last sample obtained. On the other hand, major indigenous members of the intestinal microbiome, such as Bacteroideaceae, orange one here, and Lachinospiraceae, here, brown one, have relatively decreased. Here is a result regarding change in ileal microbiota composition after BFM single ingestion. As you can see by comparing with LCS data shown in the prior slide, BBRY transited the gastrointestinal tract more slowly than LCS. And except in subject B, BBRY did not persist as long. In addition, its relative abundance was lower than that of LCS. It's a result after LFM and BFM simultaneous ingestion. In subjects who ingested both probiotics, LCS and BBRY, were detected in ileal fluids at similar times. The combined relative abundance varied among the subjects and over time within the subject. In all subjects, the relative abundance of LCS was much higher than that of BBRY, except for subject B, in whom the relative abundance of BBRY was higher than that of LCS until 3.5 hours after ingestion, after which LCS was more abundant. In this study, the ileal fluids were cultured on the rich nutrient agar plate medium and cells with colony-forming ability were counted as viable cells. The average survival rates of LCS and BBRY were calculated as 8.2% and 7.8% respectively. These results mean that more than 1 billion LCS and BBRY cells reached the terminal ileum with their colony-forming ability intact. This study also revealed that LCS and BBRY passed through the upper digestive tract without colonizing or stagnating in the region. And no negative correlation was found between the bile acid concentration and the viability rate of the ingested LCS and BBRY in the ileal fluids. And additionally, as an aside, it was also revealed that Streptococcus strains living in the oral cavity reached the terminal ileum in association with the ingested fermented milk without losing their colony-forming ability. If you are interested in this, please have a read our paper which published in Gut Microbes. Finally, based on latest findings, I will present a hypothesis about host stimulation by probiotics. Normally, immune and endocrine cells in the upper gastrointestinal tract are continuously stimulated by indigenous bacteria, and stimulation by the predominant commensal bacteria is thought to be affect immune control and the gut-brain interaction. As I explained using prior slides, stimulation of host cells by probiotics and subsequent signaling have been explained by in vitro experiments and animal studies. However, there has been some skepticism as to whether probiotics can actually interact with host cells in the human gastrointestinal tract, even when a small number of probiotics coexist where miscellaneous indigenous bacteria exist. The results obtained from our study reveal the existence of the time period when the small intestinal microbiota is occupied by the ingested probiotics, indicating that there is adequate opportunity for the ingested probiotics to continuously stimulate immune cells, nerve cells, and enteroendocrine cells in the upper gastrointestinal tract based on the findings during a time period when ingested probiotics occupy the microbiota in the upper gastrointestinal tract. Stimulation by these probiotics is likely a preferential contributor to these events. Thus, our study revealed some key new findings that will help elucidate the mechanisms of the physiological effects of probiotics. As the dynamics of ingested probiotics in the human gastrointestinal tract become clearer, further progress in this research area should elucidate the behavior of these bacteria within the tract, as well as the mechanism of their physiological effects on the host. The next challenge in this research area will be to make the connection between occupation of the small intestine by ingested probiotics and their stimulation of host cells. For this, it's expected to prove whether probiotics actually contact and signal host cells in the human gastrointestinal tract. As you can see, I have many researchers to thank for their authorship. So it is with humble gratitude that I drew your attention to my illustrious colleagues. I thank you for both your time and attention. My very sincere appreciation. Thank you.
Any question for Dr. Oishi? Is there anything there or? No question. Anybody from the audience want to ask any question? Okay, then thank you, Dr. Oishi. We enjoyed your talk. Now I'll request Dr. Avasti to introduce our next speaker.
Thank you.
Good evening, all. Myself, Amit Avasti. I first like to thank Professor Ganguly for organizing this wonderful conference. So, in the continuation of the talks, now we are inviting Dr. Bruno Pott. Professor Bruno Pott made a PhD in microbiology at University Ghent, Belgium, where he performed research on lactic acetobacteria. In 1997, he joined the company Yakult. In 2001, he became research director at Institut Pasteur, Lille, France. And during that time, he was also a director at bioinformatics company Applied Maths. And since 2001, Dr. Bruno is also guest professor at University Brussels for courses in food microbiology. Since 2016, he is actually back to the Yakult as a science director for Europe. He's a member of taxonomic subcommittee for Lactobacillus, Bifidobacterium, and related taxa, and president of the Probiotic Research Institute, France. So with this, I would like to invite Dr. Bruno Pott to please give his talk. Thank you.
Thank you, Dr. Avasti, for the very nice introduction. It's been a pleasure for me to be invited to this conference. And as the previous speaker, I also regret that not being able to be physically in India, where I have, of course, from other conferences, very good experiences. So let me share my screen and start the presentation. Sorry, something's wrong here. I hope you can see the screen now. So this is the short composition of my talk. So, well, first part, the definition has already been introduced by Dr. Oishi, so I will be quick on that. But I will focus specifically on the functionality of probiotics in terms of interaction with the immune system. And in the theme of this conference, of course, in the interaction against viruses with a particular attention for the COVID situation. So just briefly for the definition, it is worthwhile mentioning that the definition has been standing for over for over 20 years at this stage, in the sense that it was first introduced by the WHO FAO working group, which was composed around that topic, and was more recently in 2014 confirmed by a working group which was composed of the International Scientific Association Pro and Prebiotics group of experts. And actually the definition is indeed very, very easy, but also very clear. Live microorganisms in adequate amounts can confer a health benefit on the host. And the intention of my talk, of course, today is about health benefits. So if you look to the potential health benefits of the microorganisms, which are called probiotics, you can see there's really a big range of potential applications. If you can see on the left side of the slide, there is a lot of functions where probiotics have been mentioned to.
Excuse me, Dr. Bruno, could you please make your screen full, because we could not see the full screen.
Okay.
Yeah, you could please, maybe there is yeah, seems better. Yeah, thank you. Sorry for the interruption.
But this is not Can you see the full screen now? Now I cannot see it anymore, but that doesn't worry. So
so if you can make a slideshow there, maybe we can see better, but yeah, it's not full screen. You can press F5. Press F5. That's
but I have
Indian
the
way.
screen, but the problem is I have another screen. Just let me stop sharing and share again.
Okay, this is better. You may continue. This is better.
Must be screen 2. That will be much better, and then I will. I hope that's better now.
This is okay, great.
Can you hear me still?
Go ahead.
Hello. This is good. This is good.
Just go ahead.
So I was talking about the different application fields for probiotics. So what you can see in this slide, of course, is on the left side a large number of applications. And to the extent that people have wondered, is it all possible for probiotics? Can they really do the job? So in a way to understand why that would be possible is to consider three things. First thing is that, of course, we're talking not about one strain, but about many potentially different strains. That means all of them come with the specific characteristics, and they may actually have different effects. A second reason to understand why the flexibility is so high is to think about the active domain where probiotics will be working on, and that is the microbiota. And the microbiome also has been linked to many, many different aspects of health and disease nowadays. And a third reason is actually on this slide, where you can see the different effects and the different mechanisms that have been described for probiotic activity, going from microbiological interactions over, of course, immunological effects, which we will talk much further more in detail later in the talk, through barrier effects, neurological effects, metabolic effects, physiological effects directly with the host. So all of these activities can actually explain why probiotics really have a potentially big application field. Now, in the paper that was already mentioned from 2014 of the ISAP working group, they actually tried to classify these different activities into three main groups. So some of the activities are known to be widespread. Let's think about the formation of short-chain fatty acids or lactic acid, which are common to many, many different bacteria. Over some characteristics which are more maybe species related, is less widely available. Then think about the vitamin synthesis, or maybe the production of bacteriocins is also very common in a number of bacteria, but not all probiotic bacteria. And then the third category, which is of interest of the is really those characteristics which are strain specific. They are really rarely found in strains, and you need to really a specific selection procedure to come up with those strains that have those characteristics. Of course, the immune system or the interaction with the immune system is one of those characteristics. And when we talk about the gut and immunity, it's obvious to do so. If you see this slide, that gives you an idea about the importance in different aspects of the immune system in GI diseases, in gastrointestinal diseases. And of course, you have below the immune-mediated diseases, which are directly like inflammatory bowel disease, Crohn's disease, as an example. Also, we can count cancer to that possibility, because also cancer is a direct consequence of a failing immune system. Of course, also infectious diseases. So taken all together, it's easy to say that like 2/3 of the gastrointestinal problems do have some kind of link with the immune system. So it's easy to discuss about the immune system. There's a lot of things are known about the immune system, especially around the gut. We know that 70% of the immune performance of our body is situated around the gut, which is quite impressive. But what is even more impressive is to realize that this immune functionality is closely linked to many other functionalities in the same gut. So immunity is linked to, for instance, the microbiology, because the microbiology will determine the composition of the intestinal gut, of the microbiota, which of course is directly linked to the immune effects. This also fairly links with barrier. So if you have a strong barrier, fewer bacteria will actually try to go through the intestinal barrier and be in direct contact with the immune system. So bacteria can have an effect on tight junctions, which can fortify the barrier. Metabolic effects are also important. If you think about the possibility of cross-feeding from prebiotics, for instance, you will get the promotion of certain parts of the microbiota, which again will have an impact on the immune system. Neurological effects and endocrine effects might also indirectly all play a role in determining how the immune system will react. And I will come back on this later on. But of course, we like to make things simple in understanding, because we still have to try to make decisions on the selection of the strains that we want to use in for instance, probiotic applications. So that's why I appreciate this image, which actually shows that roughly there's two ways that bacteria will interact with the immune system. So on the one hand, you have, let me call them the bad bugs, because they will be the cause of pro-inflammatory interactions. But as already shown by Dr. Oishi just in front of me just before, this is not necessarily meant as a pathogen, but it could also be some probiotic bacteria might actually have the potential to stimulate a pro-inflammatory, a rather pro-inflammatory response, for which the cytokine, the key cytokine that we will follow up in the following slides, is actually interleukin 12, IL-12. In contrast, you have a second type of bacteria, definitely also amongst many probiotics, which will not have a pro-inflammatory, but rather an anti-inflammatory effect. And their benefit is that they actually also will promote tolerance. And by increasing the Treg cells to develop in the gut, the key cytokine for these anti-inflammatory bacteria is IL-10. So how do we select those strains actually? So that is actually not so difficult. You can use human blood. Preferably you will merge a number of donors together in order to have an average picture, because again, individual differences do really matter. You will just isolate the white blood cells by centrifugation over a fecal gradient. You can harvest these white blood cells, bring them into contact with your bacteria, incubate them for 24 hours in the right conditions, and then measure the cytokines that are being induced. So the cytokines induced, as I mentioned, the key cytokines are IL-10 on the one hand and IL-12 on the other hand. If you do this on a large number of strains, that is the picture you can get. So what you see on the left side is the results obtained with IL-10, and you see two, I would call them model strains that I pick for the rest of the discussions. You can see an L. salivarius strain, which has a high potential to induce IL-10, and a strain which has a much lower potential, the L. acidophilus strain. What you would expect is if you go to the IL-12 induction, that exactly the L. salivarius, which has a high IL-10 potential, has a low IL-12 potential. That's exactly what we see. On the contrary, you can see a low potential for IL-10 on the Lactobacillus acidophilus strain, while a high potential in IL-12. You can see that there's a big homology between IL-12 and interferon gamma. Both are considered pro-inflammatory cytokines, and that the picture for TNF-alpha is much more stable for the different strains. Now, to fortify that observation, one can calculate the IL-10 to IL-12 ratio as measured on these blood cells, peripheral blood mononuclear cells. You can see that then you can actually fortify the picture, and you can clearly discriminate strains which we would call anti-inflammatory strains from strains that do not have that potential. Also interesting from this slide is that this is really strain-specific. So you can see here two Lactobacillus casei strains, which both have a completely different profile, one being anti-inflammatory, the other one being not inflammatory at all. Now, this is, of course, all in vitro work, and one can ask the question, to what extent is this also working in vivo? So what we did in Pasteur Institute in the past was actually use those strains in measuring the protection of mice when they were inoculated with TNBS, which is a chemical agency that will evoke colitis. And what you can clearly see is that the strains which have in human blood a potentially high IL-10, IL-12 ratio, they will protect the mice against inflammation, while those strains which don't have that potential, they will actually not protect, and in some cases even worsen the colitis. So can we use this in terms of fighting viruses? So what do we know related to that? So viruses we know are responsible for over 90% of the respiratory tract infections. There is evidence that a disturbed microbiome, which we call dysbiosis, both in the gut and in the lungs, can actually negatively affect the course of a viral disease. And this will be even worse or very typical for people that previously have been treated with antibiotics, also for elderly people and people with chronic disease, because most probably in those people, the microbiota is already disturbed. Studies suggest that using probiotics can actually aid in the prevention and the reduction of the severity of respiratory tract infections. So a more recent meta-analysis published in May 2020 showed, with 6 studies being compiled, that probiotics can have a significant reduction in infection risk. That is in a preventive aspect. The quality of the evidence, however, was considered low because of publication bias and also because of substantial heterogeneity between the different studies. A more recent paper, even from this year, has reviewed 27 clinical trials with over 9,400 patients with respiratory tract infections for the potency of probiotics to treat respiratory tract infections, so not prevention, but treatment. In this study, also 10 ongoing clinical studies of probiotics intervention with COVID-19 patients has been included. And the results of that study were positive in the sense that they show that probiotics could significantly increase the plasmid levels of cytokines, increase the effect of influenza vaccine, increase the quality of life according to questionnaires that have been launched, but also reduce the viral titers and reduce the incidence and the duration of the respiratory tract infections. So the final conclusion was that probiotics can be recommended as an adjunct therapy to prevent COVID-19 in a preventive strategy, but also as a rational complementary treatment for respiratory tract infections, also possibly for COVID-19, and that would be a viable option to support a faster recovery. Now, what would be the different mechanisms that are underlying? And I would like to focus on what was recently published in this, first of all, in COVID-19 situation. So as was explained very brilliantly by Dr. Pillai, the mechanism of the infection goes through the angiotensin converting enzyme 2. So the virus is definitely, this is the entry of the virus. But what is interesting is that Cole Jeffrey and collaborators already in 2015 have shown that the angiotensin converting enzyme 2 could have a positive impact on cardiopulmonary health by improving the endothelial function. And that this beneficial effect can potentially be mediated by changes in the microbiota. So probiotics having an effect on the microbiota would be one potential first link of how probiotics could intervene with the infection process. Following an infection with SARS-CoV-2, what we saw, and was also explained in the former presentation, is that we see a highway of immune responses in the lungs with excessive amounts of pro-inflammatory cytokines like interferon. So this has been called the cytokine storm. And the resulting inflammation leads to a major dysfunction of the lung and to the severity and contributes to the severity of the disease. The high mortality observed in COVID-19 patients, or in some of the COVID-19 patients, therefore appears to be primarily depending on this unsuitable immune response from the host, where it seems immune regulatory systems have not been able to put themselves into place, and the pro-inflammatory activities are prevailing. So getting back to what one of my previous slides, one of the questions that can be raised is whether it is possible to put in the fight, the probiotics, with the potential to actually turn down inflammation with a regulatory and a tolerating profile. So if we decide to do so, how could this explain actually that an intervention in the gut would actually have an implication in the lungs. So also quite a lot of research has been made available in that area, substantiating the fact that there is a gut-lung axis, not only related to the microbiota, where the link is quite obvious and has been proven in the past, but also about the functioning of the immunity. So gut and lung immunity clearly are linked in a bidirectional way. It has been shown that if there would be a dysbiosis in the gut, that this also has effects in the lung. And this is actually what has been observed in a number of COVID-19 patients. I will come back on some of the observations in the coming slides. So pilot studies have indeed been performed to make an inventory of these microbial changes during a COVID-19 infections, both in the gut and in the lungs. And some tests with pro and prebiotics have been started, pilot studies, to actually investigate the potential of treating those patients with those agents in order to intervene with either the microbiota or the immune aspects of the infection. So what do we expect actually from the literature? Because this is a very recent research domain, so there's not so many published studies which actually already give us a yes or no answer. But what we can expect is based on many, many studies that have been done in the past. I already mentioned a few reviews that have been published. And what we can learn from this is that there are several mechanistic hypotheses that we can put into the picture here. There would be, first of all, the potential of probiotics to reduce the intestinal permeability, so preventing secondary infections to get the patient more sick. Strengthening of the innate immunity and the mucous membranes, the action on the adaptive immunity, and the specific stimulation of natural killer cells, which would also has also been put forward, and I will come back briefly on that later on. So many of these mechanisms are really interesting in terms of considering an additional adjunct treatment for COVID-19 patients. But the studies to date, as I said, have been rather small, and they have not been really convincing enough in terms of the number of patients that have been treated. However, the observations that have done look quite promising. There was a decrease observed in the numbers of lactobacillus and bifidobacteria species in some of the patients with COVID-19. You will know that these are the most promising and the most prevalent probiotics in the market currently. And some tests with a nutritional approach using pro and prebiotics also suggested that these interventions would support the regulatory immune arm, would actually avoid or correct the dysbiosis, which has been noticed in COVID patients, and which could be due, for instance, to also the intake of antibiotics. But also a positive result in reducing the risk of secondary infection linked to bacterial translocation, so the fortification of the intestinal barrier. Modulation of intestinal microbiota, for instance, therefore, through probiotics, maybe even prebiotics, and one of the suggested topics was also fecal transplant, could actually help to regulate the uncontrolled inflammation, which is one of the biggest symptoms or the biggest problems with severe COVID patients. So what do we know so far as a first summary? So we have seen microbiota changes in the gut linked in COVID-19 infection with a reduced diversity and a reduced richness of the bacteria, with reduced numbers of bacteria that produce butyrate, which is very important also in maintaining immune functionality. So Faecalibacterium prosnitzii, Lactospiraceae, but also Eubacterium has been shown to go down. An increase of some potentially pathogenic bacteria like Streptococci, Rhodia, Veillonella, and Actinomyces, and a clear indication of a failing immune system, also the going up of yeasts and potentially pathogenic fungi. Similar observations have been observed also on the level of the nasopharynx, where also the biodiversity is going down, and in particularly lower levels of Caranibacterium accolens, which is known to release anti-pneumococcal free fatty acids, and so that's considered a negative evolution. There was also a mention of an increase of Propionibacteriacea, the result of which, or the effect of which, is not very clear currently. COVID-19 patients have also a changed microbiota in the airways with presence of potentially pathogens like Actinobacter, Chrysobacterium, a large set of bacteria, which normally should not appear in the lungs. But what do we know concerning the immunity part? Well, we know that probiotics, at least some probiotics, as I mentioned initially, should be careful about the strain specificity. They have the potential to increase type 1 interferons, antigen-presenting cells, natural killer cells, T and B lymphocytes, both in the intestines and in the lungs. And as we know, these immune functions are really what we need to fight a viral infection. So they could potentially assist in limiting the lung cell damage and directly or indirectly contribute to the elimination of the virus or the infected cells. So one author or a couple of authors particularly mentioned the use of bifidobacteria in reducing inflammation in this context. So since these activities are really considered as more pro-inflammatory, they might actually help to fight the viruses. In this case, of course, they should not contribute to the cytokine storm, and therefore their application should be situated maybe in a preventive stage. Once the cytokine storm has actually launched, then probably you need another type of probiotic, or you may take benefit from another type of probiotic, which has a very thorough anti-inflammatory and regulatory function. So it will stimulate these arms of the immune system, stimulating regulatory T cells as a primary topic, using mainly the cytokine IL-10, which is responsible for launching most of these tolerance and regulatory cell activities. And these would, of course, be active again once the cytokine storm has developed. So this is much more on the treatment level. So unfortunately, there's not so many studies available yet to test this hypothesis. And there is one study with 8 probiotic strains that has tested the probiotic effectiveness, and they confirmed, very small study, that the probiotics have a potential in reducing the risk of respiratory failure, the reduction of reanimation cases, and reduction of the mortality in the treated group. So if you want to read more details, you can read, of course, this paper. Clearly, the conclusion from this aspect is that we need much more clinical studies to confirm these preliminary results. Still, I would be very optimistic because there is other mechanisms that have been described for probiotics which directly or indirectly interact with the immune system. And I like this Nature Reviews article in Nature Reviews Microbiology, because it's a simple scheme that shows us the large mechanisms, the overall mechanisms by which probiotics can interact with the immune system. Some of them are relevant for fighting viruses. So one of them is the NK cell activation, natural killer cell activation. And another one, of course, is the stimulation of immunoglobulin production, secretory immunoglobulins, which will eliminate directly the viruses. So one is after infection, eliminating infected cells, and one mechanism is eliminating the virus, the free virus. So I'm not going into details, only talk of 25 minutes, but like to give you one example of a study that has been done in order to test both potential mechanisms. It's very difficult in healthy people to show effects of probiotics, and that is what, if you talk about a food, what food authorities would like you to do. But this is a very interesting case in a sense that Professor Gleason, he worked with athletes in a wintertime period, which because of their training program, very severe training program, actually see their immune system going down. That plays both on natural killer cells as well as other aspects of the immune system. So he invited those athletes to actually participate in his study, in which he used the strain Lactobacillus casei shirota in 32 patients. And he compared them, well, not patients, athletes, I should say, because they're healthy people, of course. But he compared them to 26 athletes that got a placebo. And the results were quite interesting because the first results showed that not only the the number of infections was reduced, but also the time of infection was reduced, which actually supports the fact that probably the virus that causes, like I said, 95% of the respiratory infections was actually managed either by increased natural killer cell activity, also by this result, the second result, by an increased IgA, salivary IgA in the saliva, which, as you can see from this slide, was significantly higher in the LCS group rather than the control group. What is important in this slide, though, is that the IgA levels did not go up during the treatment with the probiotic, but actually the probiotic prevented the salivary IgA concentrations to go down, probably because of, one, the winter season maybe, and second, also the hard training program, which puts the system of, in this case, the athlete. And so the probiotic can help to support normal levels of these secretory IgA. So just to show you again that research in this area is not so easy, this is an overview of studies that have been done all with the same probiotic strain in different parts of the world with different types of population, and in which natural killer cell activity was actually monitored. And what you can see is that in many cases you can see a positive effect, but in a few cases, study in Germany, study in the Netherlands, there was no difference. And you remember the slide that I showed where the complexity of the immune system is linked actually to many other different activities that have to be also in line with the immune system activities, and in order to confirm an effect. And that is also probably the difficulty we are facing if we are doing experiments with probiotics in a wider population, and it's very difficult to control all those additional conditions. And this is why it is necessary to do not only one study, but multiple studies, and try to compile all that information and present it through meta-analysis, which will give you a much clearer and a much more reliable picture about the feasibility of the results. So this brings me to the last slide, my concluding slide. I think this is an interesting picture of what is actually happening, also for COVID, but not only for COVID-19, but also for other types of lung infections. And what you can see is that definitely we are now convinced that there is a link between the gut and the lungs in terms of microbiota and in terms of immune system. Studies that link COVID-19 with the gut and its microbiome have shown that there is differences induced in the disease phase. So you can call it a dysbiosis, and this dysbiosis is known to contribute negatively to the course of the disease. We know that the microbiome will significantly affect the immune response, so we can take advantage of that. Because in some cases, for instance, in elderly, in obese people, in people that are chronically ill, we know that the microbiota is damaged and that probiotics can help to restore or at least diminish the dysbiosis. And of course, what we see is that also the same population is actually prone to more severe effects of COVID-19. So there is a hypothesis that definitely needs to be further tested. So that hypothesis, as you can see, will play in the right part of the slide, you can see, will play on the diversity of the microbiota. In the upper part, green arrow, the diversity of the microbiota, the junctions, which actually will fortify the barrier so that pathogens or results of drug administration, antibiotic administration in those patients will actually be minimized. Also, of course, the fact that some selected probiotics will be able to stimulate this regulatory cell response, Treg response, which may help to soften the cytokine storm, which has been the cause of more higher levels of mortality and morbidity within infected patients. So with that in mind, I would like to thank you very much for your attention, and I hope that I will be able to answer your questions.
Thank you, Dr. Pot, very much for very interesting talk. Any questions from the audience? Dr. Bhabatos is having questions, so please.
Me? Okay. So I have just two important questions. The first question that I'm going to ask you, can probiotics then uptake DNA from the opportunistic pathogenic bacteria living in the gut and become virulent? Because if the probiotic strain is naturally competent, they always have this possibility to take DNA and become virulent. So what is your opinion on that?
I'm really sorry. I didn't hear the last part of your question. Can you please repeat?
What I'm asking, since most of the probiotic strain, they're naturally competent, so they can uptake DNA from the gastrointestinal tract from the opportunistic bacteria, and they become also virulent. So is there any study or is there any data to show that probiotic bacteria do not change their genome depending on the subject or depending on the gut microbiota composition?
So still the connection is very bad, but you said that is it possible that probiotics take up DNA and therefore they change their behavior? That is, yeah.
That's
okay. Yeah, so it's an interesting question. So there is not so much research that has been done on this. And there's two things I would like to say. First of all, the risk would be that they take up, for instance, antibiotic resistances from potential strains that have antibiotic resistances. Therefore, I think probiotics have been selected first of all the probiotics on the market for their the absence of the antibiotic resistance. So themselves, they will not contribute to that. This probably also means, if they have been selected, that they are less prone to take up some of these antibiotic resistances. So I would say the fact that they don't contain them might be, it's not a guarantee, a reason for them to have sufficient resistance against the uptake of foreign DNA. So that goes for antibiotic resistance, but it might also go for other types of DNA. The second thing I would like to say is that, and that is interesting, is that probiotics might actually express a number of genes that, since they have been selected also to survive the gut, to survive the passage, they might actually produce bacteriocins or other kinds of bacteria, which will also, or other kinds of molecules, which will also reduce the chance of taking up foreign DNA. However, to answer your question in the fact that they do take up some DNA, it's also interesting to know that FDA has banned the use of probiotics which are permanently colonizing. So all of the products on the market today, they will actually not permanently colonize. So that means if they would actually take up foreign DNA and become dangerous, and the problem can be assigned to the probiotic taken, then just stopping the intake of the probiotic should actually eliminate the strain from the gut in less than a week. This is what is a normal observation. Some take longer, some take less long. Does that answer your question?
Yeah, very much. Amit, can I ask one more question?
Sure. Please.
The second question, do the effect of the specific probiotic strain depend on the gut microbiota enterotype? So the people living in India or Europe or US, they have the different types of gut microbiota and definitely different types of enterotypes. And
Yeah.
do you think that the same probiotic strain will serve equally well to all the populations?
Yeah, it's an interesting question, and it's a question that I always get when I come to India, and I don't get it anywhere else. It really is very fascinating that you are very worried about needing Indian probiotics for the Indian population. My answer is twofold again. So on the one hand, I realize that the diet in India is different from other parts of the world. And therefore, I think the way that probiotics will interact with the rest of the microbiome will be different. Having said that, I think as Dr. Oishi showed, you can have a survival of a particular strain in different parts of the world. So he showed that in different parts of the world, the LCS bacteria was actually surviving the passage through the stomach. So depending on the fact that, independent of the fact that the diet is different, the bacteria have mechanisms to survive the passage and to establish itself in the intestine. Now, my estimation about the literature that I went through, that's the second thing I want to say. My interpretation is that sometimes in the differences between individuals within the same geographic location is higher than the differences between the different locations. So that means that if your theory would be right, that we need particular Indian strains for an Indian population, you probably need your own individual strain to be active, because there is your microbiota is definitely different from mine, but it might be as different from mine as it is from your neighbor, who is having more or less the same diet as you have. So I think that the diversity within the microbiota is really high, and the practice shows that particular strains will be able to establish in this diversity of microbiota compositions, despite the fact that these differences are real.
Thank you, Bhavatos. Professor Ganguly.
Dr. Bruno, one of the studies which was, this was very interesting, 2 points you made were very interesting. One was that the US FDA has made this stipulation that they should not permanently colonize. And so this particular part still forms a very important part of the Indian probiotic regulation. So somewhere we need to remove that because it creates the same problem as we have seen, that the organism transform within the gut, and that transformation will ultimately affect the health. One of the questions was this, that I was at one time I was working with psoriasis, an inflammatory disease, and we were struggling for a biomarker where we will know that whether the drug is acting or not acting. And we found that interleukin 10 was that biomarker, and the ratio of interleukin 10 and 12 showed the functionality of that. So this was a very interesting data which you had shown, that this variation, cytokines actually show a lot of diversity when you measure, particularly in India. And when you measure that, you don't find correlations often, but your data showed a beautiful correlation. And in the psoriasis data, we had seen the same. So I think this should be used more often in the COVID versus probiotic and others to measure whether the thing is working or not working, apart from interferon and NK cell diversity. My final question of yours about Indian strains and other strains, Dr. Gorbach at one time carried out the diversity of the Indian gut the bacteria. Indian gut has got millions of more bacteria than your gut. And we also have many more bacteria in our upper gut. Your upper gut do not have those many bacteria. So we might need, Dr. Mehra says we have no upper gut, but that I totally disagree with him. So the competency might vary, but essentially I don't believe that we could have an Indian probiotic and a Belgian probiotic, because at this given moment, whatever we have done, we have studied probiotic strains as a universal probiotic strain.
Well, let me first comment on the fact that I have less bacteria than you have. I'm actually convinced. I'm part of 3 initiatives where we want to actually show that the diversity which we take from the diet is really essential. So we have 3 initiatives, one by IPA Global, one by ILSI North America, and one by ISAB, who are all interested in creating what we have called so far the dietary microbes category. So everybody knows about dietary fibers and the importance of that for health, but nobody talks about dietary microbes. And still we're convinced that fermented foods specifically are really interesting and really necessary to feed the diversity and to keep our microbiome healthy. And in the Western diet, as you rightfully suggested, we have lost a lot of fermented foods. We have lost a lot of those diversity, and not only the diversity, but as you also rightfully said, the numbers may have gone down. And that is supposed to, on the long term, I think behind a number of observations like more, a higher level of allergy, higher level of non-communicable diseases. And what we would like to show is that indeed with geographical comparisons like diet, performance or the presence of those non-communicable diseases in India, where the diet is rich in live microbes, and Western diet, that this would be an argument also for the government to say, well, let's create this category and let's add it to dietary advices and dietary recommendations so that everybody is aware of that particular issue and is consuming worldwide much more live microorganisms. But this is the first steps, but we're hopeful we can get there.
Professor Mehra, please.
Thank you very much. I just want to ask you, and my question will be much shorter than that of Dr. Ganguly. I wanted to ask you about the disruption of host immunity that we see in COVID-19. In particular, you see there is a hyperactivation of the innate immune system and hypoactivation of the adaptive. So is there any evidence from your studies or from others that the microbiota helps to treat this disruption in one way or the other, that particularly this cytokine release syndrome is taken care of?
So thank you for the question. So the answer is there is no convincing clinical study available today. That I want to make sure. So there's only this small study that I mentioned with 8 different probiotics, and the results are promising, but there is no large-scale clinical work that is available at my knowledge. So the only information that we have is actually linked to observations done with respiratory tract infections from the past, with results related to vaccination for influenza. So it's an indirect evidence that we can use today. So and that's one of my recommendations was indeed we need to do this type of studies in a controlled way, and it will take time. And well, on the other hand, I hope we don't get the time that we can get rid of COVID as quick as possible. So we don't get the time to do the studies, but it would be nice to have them done for sure.
I think, thank you very much. We are running short of time. And with this question, I would like to thank you very much. And now Dr. Panda will introduce to the next speaker. Thank you.
He's there already. Yeah, our next speaker is Professor Jeffrey Gordon. Jeffrey Gordon is the Distinguished University Professor at Washington University in St. Louis. He's MD from University of Chicago, and after completing his clinical things, internal medicine and gastroenterology, he did postdoctoral at NIH and joined as a faculty at the University of Washington University, where he spent his entire career. And currently, he is the founder director of University Department of Interdisciplinary Center of Genome Sequencing and System Biology. Professor Jeffrey, your turn, please.
Well, thank you very much for this opportunity. It's a pleasure talking with you. I'd like to describe a collaboration involving colleagues at the International Center for Diarrheal Disease Research and our lab, which is located in the Center for Genome Sciences and Systems Biology at Washington University in St. Louis. This collaboration, which is funded by the Bill and Melinda Gates Foundation, is, and I'm going to have a bit of a problem, okay, is directed at trying to address a global health problem, one that you know well, and that is childhood undernutrition, leading cause of death in children under 5. Many epidemiological studies have shown that undernutrition is not due to food insecurity alone, but rather represents the confluence of factors that operate within and across generations. Current therapies have reduced mortality, but they haven't had a great deal of efficacy in the long-term morbidities associated with undernutrition. And those include impaired linear growth, or stunting, poor responses to vaccines, and neurodevelopmental delays. So we're missing something, and the question is, what is that? We have a hypothesis that we've been pursuing as a team, and that is that there is a definable normal to the program of gut microbial community assembly, and that this program of community development is disrupted in children who have undernutrition. And moreover, this disruption is not simply an effect of undernutrition, but rather is a contributing cause. A corollary to this hypothesis is that healthy growth of infants and children is linked to healthy development of their gut microbiota. So, as you know, in this field, one of the most daunting problems is defining normal within a population and across populations, and then developing metrics to quantify deviations from normal, then determining whether these deviations from normal are a cause or effect of pathology, subsequently to identify therapeutic targets, and then to be able to prosecute in a pipeline therapeutics directed at repair of a microbiota. And I'd like to go through this process in the context of childhood undernutrition. So defining normal gut development is a inspiring task, but one that causes quite a bit of perspiration. Why? We have to go beyond a simple definition of component parts to looking at interactions between components. And I'll illustrate this in this slide by saying that we obviously wouldn't know the organizational properties and dynamics of a school of fish if we only focused on enumerating the individual components of that school. Similarly, for birds in flight in a flock, or ants foraging, or even stock markets. How can we identify in the midst of astronomical numbers of potential interactions? After all, if there were 100 species in the gut microbiota, the number of pairwise and higher order interactions are literally astronomical. So we have to do something for feature reduction and identify a smaller number of interacting components that could describe normal development of the gut microbiota. And we actually turned to a field that was developed to try to understand the performance of stock markets, econophysics, and the relationship between variations in various economic sectors and the price of stocks. So that particular approach involves looking at consistent covariations between members of complex systems. Our colleagues at the ICDDRB, led by Tamid Ahmed, turned to a birth cohort that was studied who lived in an urban slum in Dhaka. This birth cohort was followed from month 1 postnatally, initially through the first 24 months, and then subsequently through 60 months with monthly fecal collections. The initial data collection involved simple 16S based analysis and a focus on healthy members of this birth cohort, members that showed consistently healthy growth as defined by anthropometry. And Arjun Raman, who is a very talented MD PhD postdoctoral fellow in the laboratory, applied these methods from econophysics and identified a small group of 15 covarying strains that could describe normal community development in healthy members of this birth cohort living in Mirpur, the urban slum in Dhaka. We extended this analysis of these taxa and this approach to other birth cohorts living in other areas of the world where the burden of undernutrition was great. And we're fortunate enough to collaborate with Cherry Kang at CMC Vellore and looked at a birth cohort there and found that these 15 covarying strains could describe normal community development in that cohort. And that was true in several other cohorts. So we have an operational definition of normal community development using these groups of organisms. By no means are they the only organisms, obviously, in the developing gut microbiota, but applying these taxa, which Arjun termed an eco group, found that the development or maturation of the gut microbiota was completed by the end of the second postnatal year in these healthy children, largely completed. And the children with undernutrition, children who presented with moderate acute malnutrition or severe acute malnutrition and were wasted, had immature gut microbial communities. That is to say, their microbiota configurations look like that of children who are chronologically younger than they were. Interestingly, this immaturity is not repaired by current nutritional interventions, at least in several studies that we have performed together with our colleagues at ICDDRB. And that's perhaps not surprising because current nutritional interventions for undernutrition were not fabricated based on a consideration or a deep knowledge of the developmental biology of the microbiota. So we can think about these children with moderate and severe acute malnutrition. And by the way, immaturity is greater in children with severe acute malnutrition than moderate acute malnutrition, as having a persistent developmental abnormality, one affecting one of their organs, the microbiota, that has not been ameliorated with current interventions. A test of causality. If these taxa can be used to quantify degrees of disrepair of the microbiota, how can we determine whether these immature communities are an effect versus a cause of many of the manifestations of undernutrition? So for that, a test of causality involving the transplantation of microbiota obtained from chronologically age-matched children, a group of the samples coming from children who have normal growth phenotypes as defined by anthropometry, and another group of samples coming from children who have significant growth faltering and immature microbiota. And the question is, to what extent can the phenotypes associated with undernutrition be transmitted to young, just weaned, germ-free animals who are fed diets representative of the donor population? And these studies, performed in our Notobiotic facility here in St. Louis, revealed that immature gut microbiota can transmit a number of features associated with undernutrition to these young recipient mice. And those include impaired lean body mass gain, as defined by quantitative magnetic resonance, impaired bone growth, as defined by microcomputed tomography of their femurs, impaired metabolism, as defined by mass spectrometry based analysis of a number of analytes in various tissues, and impaired immune function. Now, Laura Blanton, who began these sets of experiments, when she did so, applied machine learning algorithms to identify among all the groups of mice that received these various donor microbiota, whether there was any growth-associated bacterial strains. And she identified a series of growth discriminatory bacterial strains whose abundance or fitness was correlated with various aspects of growth, including lean body mass gain. It turns out that these growth discriminatory strains are a subset of the eco-group taxa and also of several other strains, and that many of these are underrepresented and presumably underperforming in the immature microbiota of these children. So after a definition of normal, after developing ways of measuring deviations from normal, and after this test of causality, we had an opportunity to define our therapeutic targets and to focus on these underrepresented and presumably underperforming taxa in immature microbiota in children who presented with moderate acute malnutrition in the age range of 12 to 18 months. So we had to think of a variety of different ways of intervening. One, of course, would be to culture these age discriminatory strains and create a next generation probiotic consortium and add it to immature microbiota. And we did that, Laura did that, and transplanted the ensemble of the immature microbiota plus the probiotic consortia to young germ-free animals. The control animals only received the immature microbiota and showed that there was amelioration of a number of these phenotypes associated with undernutrition. But the development of a probiotic consortium of anaerobes would be complex, as you all well know. The regulatory pathway would be difficult, and the ability to scale this would also be challenging. So we sought to find a culturally acceptable, affordable, scalable intervention as a first type of therapeutic initiative designed to repair the microbiota of these children with undernutrition. And our hypothesis was that complementary foods, the foods that are administered during the period between cessation of exclusive milk feeding and a fully weaned state, may contain key nutrients that are coveted by some of these underrepresented and presumably underperforming growth-promoting organisms. So Jeanette Gehring, a very talented PhD student, Sid Venkatesh, a postdoc, Hawei Chang, a PhD student, Michael Barrett, and Tamid and his team got together and we took an inventory of complementary feeding practices in Mirpur, this urban slum, and then began a screen involving notobiotic mice, initially colonized with cultured sequence members of the microbiota of children living in Bangladesh, representing different stages in community assembly, including both the age discriminatory and growth discriminatory strains, and sought to identify complementary foods that possess nutrients that would specifically increase the abundance of organisms that were prominent during this period of complementary feeding in healthy individuals, but underrepresented in our undernourished children. So that screen, initially conducted with a defined consortium of organisms, and subsequently with immature microbiota from children with moderate acute malnutrition, revealed a series of complementary foods that could repair the microbiota, at least in these notobiotic animals. The beauty of using the notobiotic animal model is that we can not only look at fitness, but we could also do mass spectrometry. We can look at gene expression on the part of the community member to try to understand which organisms were consuming which particular nutrients and how certain combinations of complementary foods could represent potential therapeutic leads. And in fact, we identified such lead microbiota-directed complementary food prototypes from our notobiotic mouse experiments, and had to make a decision about whether we would move from these preclinical models, which after all incorporated the microbes of the target population we wanted to treat and the base diets of this population, to an intervention that was designed to affect the developmental biology of humans. And we felt that it would be most prudent to test efficacy in a second notobiotic animal model that would more closely approximate the physiologic and metabolic features of humans, and therefore turn to notobiotic piglets that were colonized with these microbes and used to test a series of our lead microbiota-directed complementary food prototypes, or MDCFs. So from that effort, we turned to a initial proof of concept study, but it really is a pilot study to determine whether some of these MDCFs would be able to repair the microbiota of children who presented with moderate acute malnutrition, and whether there would be health benefits. So this study design, shown in the upper left, involved a small number of children, 15 per arm, 4 arms, that would test 3 of these microbiota directed complementary food prototypes, which we'll label MDCF 1, 2, and 3, as well as a commonly used food-based intervention from children with moderate acute malnutrition, ready-to-use supplementary food, which was a rice and lentil-based formulation with some milk powder, which again was not designed based on a consideration of or knowledge of the developmental biology of the gut microbiota. So these children were enrolled. There was a run-in phase where fecal samples were obtained, anthropometric measures were obtained, and just prior to the intervention, a blood draw was performed to obtain plasma, to measure using an aptamer-based proteomics platform, the levels of 1,305 proteins. And I'll get to that in a second, and why we wanted to do that. The intervention, as I said, was short, 1 month. Fecal samples were obtained weekly. At the end of the intervention, a blood draw, anthropometric measures, and then a 2-week follow-up. Now, it was particularly important to us to be able to get a much more comprehensive definition of the biological state of these children prior to, as well as after the intervention. Why do I say that? Well, as we try to repair the microbiota, we have a unique opportunity, which is to connect components of the microbiota to the operations of various host systems and subsystems. Also, you would not describe cancer as moderately severe versus severe. The definition of the biological state of undernutrition needs to have a comprehensive definition in order to be able to stratify these populations of children and also to determine the efficacy of any intervention. So this investment in trying to look at the plasma proteome in this particular way was very important to us. So this particular trial, 1 month in duration, produced a result that was interesting, and that was that MDCF2, which was the lead formulation coming out of our preclinical models, produced a significant repair in the gut microbiota of these children with moderate acute malnutrition, much more so than any of the other formulations. And that repair was associated with a remarkable change in the plasma proteome, with alterations in the levels of mediators of bone growth, of immune function, of metabolic regulation, and even of neurodevelopment towards a healthy state. The dose that was given is shown here, and I want to point out that this was a controlled feeding study where the participants were maintained on their base diet, but twice a day the mothers would come to a nutritional rehabilitation unit located in the middle of Mirpur, and mothers under supervision would give a dose of these formulations. Again, twice a day, the average serving 25 grams, the average caloric intake 100 to 125 kilocalories. So these are the formulations: the lead MDCF2, the ready-to-use supplementary food, the 4 complementary food ingredients in MDCF2, chickpea flour, peanut flour, soybean flour, green banana, soybean oil. And note that the caloric density of MDCF2 is actually less than that of RUSF. So 1 month is not enough time to see a significant effect on clinical outcome measures that people look at, especially given the fact that this was a pilot study with only 15 children per arm. So in a soon-to-be published study conducted with our colleagues at ICDDRB, again, involving 12 to 18-month-old children with moderate acute malnutrition living in Mirpur, over a 3-month period of time, children, 60 per arm, received either RUSF twice a day in the first month in the clinic under supervision, in the second month, once a day in the clinic, the other time at home under supervision, and in the third month, twice a day at home, again under supervision, or they receive MDCF2 for that period of time. Again, anthropometry, fecal sample collection, and in this case, 3 blood draws, one at the time of initiation of the intervention, one month into the intervention, so we could align it with the previous study, and another at the end of the intervention. And the results were quite remarkable. If we look at changes in weight for length z-score, a measure of ponderal growth, you see that there was a significantly greater response of those children who received the microbiota-directed complementary food 2 versus those that received RUSF. And remember that MDCF2 is almost 20% less calorically dense than RUSF. So you might ask, what opportunities for deep learning do we have here? And particularly, can we connect the dots? Can we connect the microbiota and what components of the microbiota change as a function of the interventions? And how about the plasma proteome? And could we obtain, as a result of those analyses, mechanistic insights about how MDCF2 might produce a superior ponderal growth response? And that's exactly what was done. In this particular case, though, instead of measuring 1,305 different plasma proteins, 5,000 different proteins were measured using this aptamer-based technology developed by SomaLogic. And in the beginning, participants from both arms, all 120 children aged 12 to 18 months, were considered. And in each child's case, a correlation was plotted between changes in her or his WLZ over time and changes in the levels of plasma, a particular plasma protein. So these correlation plots exemplified here for IGF-1 for all participants would give us an idea as to how to identify ponderal growth correlated proteins in the plasma. That analysis revealed 70 proteins that were positively correlated with ponderal growth. This just tells you a summary of gene set enrichment analysis of proteins whose abundances were correlated with ponderal growth in both arms of the study. What GO terms, gene ontology terms, were enriched for the set of WLZ associated proteins. And you can see positive correlations with proteins involved here in bone growth, in certain aspects of CNS development, negative correlations, levels of proteins in ponderal growth, and these proteins being involved in immunoinflammatory states. I'll just give you a quick snapshot of the work of Robert Chen. So this is the set of plasma proteins whose changes are correlated with the rate of increase in ponderal growth that are important biomarkers and mediators of bone growth. Thrombospondin 3, positively correlated. It's involved in regulation of skeletal maturation. Cartilage oligomeric matrix protein, growth hormone, IGF responsive protein involved in long bone growth. Leptin, IGF, proteins that interact with IGF to improve linear growth. So we now have a series of biomarkers, and actually in this case, a number of mediators of growth that were identified as a result of the intervention. And I will say that these mediators are enriched. That is to say, their levels of increase are significantly greater in those children who receive MDCF2 compared to RUSF. So again, a panel of 70 positively correlated WLZ correlated proteins that we have culled from this study. Finally, let's turn to the microbiota and repair of the microbiota and what taxa, bacterial taxa, are associated with ponderal growth. So Matt Hibbard, very talented postdoc in the lab, went ahead and sought to identify WLZ-associated bacterial taxa and determine whether their representation was significantly increased by MDCF2 compared to RUSF. Again, initially, all individuals are considered in both arms to try to get an idea of these beta WLZ associated bacterial taxa. linear mixed effects modeling was performed. And we obtained from such an analysis a group of 23 bacterial taxa whose abundances are significantly associated with ponderal growth, 21 of which are positively correlated, 2 of which are negatively correlated. In this plot here, the coefficient beta in the x-axis represents the change in WLZ for a unit change in abundance of one of these taxa. And you can see the most positively correlated taxa, Faecalibacterium prausnitzii. We have 2 negatively correlated taxa. Again, the age range is 12 to 18 months for these children with moderate acute malnutrition, Bifidobacteria species and E. coli. And MDCF2, it turns out, just with the plasma proteome, significantly increases the abundances of these positively WLZ associated bacterial taxa and decreases the abundances of prominent negatively correlated taxa, which happens to be a bifidobacteria. So we have intervened and altered the configuration of a microbiota, repaired it towards a healthy state. Those beta WLZ correlated taxa, the positively correlated taxa, were our therapeutic targets, and the initial development of MDCF included the age and growth discriminatory strains, members of the ECO group. We want to determine the durability of this repair of the microbiota, as well as the alterations in ponderal growth and the plasma proteome. So therefore, we're following these children post-intervention over a 4-year period of time with fecal samples, anthropometry, measurements of the plasma proteome. We want to connect components of the microbiota with the functioning of different host systems, including bone biology, metabolic regulation, immune function, and neurodevelopment. This particular type of intervention provides support to the hypothesis that I described to you earlier, which is healthy growth is linked to healthy development of the gut microbiota, and certainly causes us to look at human postnatal development, perhaps from the perspective not only of, as is typical, our human organ systems, but also our microbial communities. It also illustrates the very broad effects of the microbiota on many aspects of growth, as read out by the plasma proteomic responses. It also allows for a perhaps better definition or a more evolved definition of wellness for infants and children, with implications for preventative medicine. In this window in the first 2 years of postnatal life to intervene, if we can quantify deviations from normal in the development of the gut community. And such an intervention, if applied, perhaps could have long-lived beneficial effects. So a lot of our efforts are directed at now providing interventions at earlier points in postnatal life, rather than 12 to 18 months, moving earlier, and for longer periods of time. And certainly to generalize these types of trials to other populations where the burden of undernutrition is great. That will require not only the application of MDCF2, but also the development of geo-adapted MDCFs that are affordable, culturally acceptable, and have satisfactory organoleptic properties, taste, texture, and smell. And for that reason, we've returned to our preclinical models, in this case, colonized with representative microbial communities, to identify these geo-adapted MDCFs. And also the idea that MDCFs may have to be applied in different formats over a sustained period of time to maintain a healthy configuration of the microbiota. The final thing I wanted to emphasize is about prevention in the form of complementary feeding practices. So current practices for infant and young child feeding are not predicated on a consideration of the developmental biology of the microbiota. And the types of studies that I've described to you during the course of the last several minutes also serve as a foundation for identifying a series of foods that could be administered at different phases during the complementary feeding program that are adopted by parents around the world, to make it more likely that microbial community development proceeds in a sustained and healthy manner. So how can we be more effective stewards of our children's precious microbial resources? So I thank you for your attention and be happy to answer any questions.
Thank you, Professor Jeffrey. Any question, Professor Ganguly?
A very interesting study. I'm Nirmal Ganguly. I am in the ICTDRB Scientific Advisory Board and had studied this work which you have done and published in one of the best journals in the world, and was very, very intrigued that you have been able to move from notobiotic animals to humans. And this was a path-breaking study because Dr. Yagnik, who is in Pune, had also a food with the microbiota, but it didn't succeed for improving the growth of the children, linear growth of the children who were underweight and malnourished. One of the suggestions which I have to you is that this RUS, which Tamid has done very large studies in Bangladesh, that is the ready-to-use supplementary food, and this is liked by the children. Previously, I asked him, "Is it khichdi, which is salty?" He said, "No, this is halwa. It is very nice tasting. Halwa is a delicacy in Indian subcontinent." So it will only tweak a little bit of your MCBF2 to make to turn into the second version of the RASP, and the safety and the desirability of RUF has been seen in such a large population. It will be very, very successful. So this is my suggestion to you. I don't know how you take it.
I really appreciate your question and your points. We would love to do a study of MDCF in India. We'd love to return to our partnership with Cherry.
Small question. We are already late.
Okay.
No, for you, very small question. We are already late.
Thank you very much. I just wanted to ask, this was a wonderful talk. I really learned a lot from your talk. I wanted to ask you your slide, which made a question. Is gut microbiota maturity a cause or effect of undernutrition? I think that tells it all. I wanted to know whether, are there any particular bacterial strains that you're talking about? There are at least 15 you talked about. And you said that the undernutrition would actually affect several of them, and therefore, your experiments on the MCDF. Are there specific strains that you're talking about, or it could actually be the common for all ethnic groups, or is there any variability that you might have observed in one ethnic group to the other?
Oh, spectacular question. So we can take advantages of new advances in genome sciences and do shotgun sequencing of our fecal DNA preps and assemble the genomes of the different bacterial strains in these organisms to look at the strain level variation and correlate different strains and their responses based on their genome content and culture these organisms. And we've done this and are reenacting these studies in notobiotic animals with these different strains to determine the strain level sensitivity to the responsiveness and to connect the bioactive components of MDCS to the responses. We need to know the bioactives. Food science marries microbiome science. absolutely critical marriage. That is one of the things that we're pursuing. The other thing is the small, I know I don't have any time, but the small intestinal microbiota, we also think is absolutely pivotal. And we've done studies together with Tamid about environmental enteric dysfunction, identified a series of bacterial strains in the duodenum that are negatively correlated with linear growth, that when introduced into notobotic animals reenact EED. And we think that these are also key contributors to various aspects of healthy growth. Lot to learn, a lot of terra incognita to explore together.
Okay, thank you, Jeffrey. We came to the end of this session. In fact, let me tell you at the outset, I'd like to thank the organizer for selecting 3 wonderful speakers. All 3 of them really spoke well. And if I summarize, all 3 of them spoke about different aspects of probiotics. One talk about intestine, one talk about gut and similarity between the brain. The other talked about the childhood nutrition and malnutrition, how does it affect. But most importantly, if you remember now, the probiotic things is going more towards immunological aspect. Everybody talked about the involvement of immunology, mostly the NK cell and other things. And most interestingly, all 3 of them, I again really appreciate the organizers. All 3 of them use 3 different model. The first speaker, I think, Dr. Kenji used a perfusion model to know how actually the bacteria colonize. Then Bruno told about how to use PBMC to select a particular strain. And finally, Professor Jeffrey told about how actually during the developmental stage, the microbiota really helps on the growth of a child, and particularly the role of microbial directed complementary food. I think even though we are getting late, it was worth listening, and I must appreciate and thank you all. And with this, I thank my co-chair, Dr. Avasti, and thank you all for listening to this. And we close this session. Thank you all.
Thanks for this wonderful scientific session. I request the felicitation process. So requesting Professor Panda to kindly felicitate Dr. Avasti. Everybody please put your hands together. Thank you so much. Yeah. So ladies and gentlemen, thank you so much for being a wonderful audience. So before we close, I would like to request you please join us for the group photograph and dinner in the foyer area. Thank you so much for being with us. Please join us tomorrow at 10 a.m. sharp. My name is Naina Baveja, signing off for this 11th India Probiotic Symposium. Thank you so much. Everybody, may I have your attention, please? Please join us for a group photograph. Everybody requesting, kindly come on the main stage for the group photograph, sir.
नहीं दूंगा यार ऐसे कैसे